On November 14th, 2023, Voyager 1 stopped talking. Not gradually, not with a stutter or a fade. One day the data was flowing, and the next day, the spacecraft had been speaking to Earth without interruption for 46 years, replaced its voice with a single repeating pattern. Ones and zeros, over and over, meaningless, like a heartbeat with no heart behind it. The carrier signal was still there. You could still hear the phone ringing, if you want to think of it that way. But nobody was on the other end. Just a monotone, just a dial tone from 15 billion miles away. The team at the Jet Propulsion Laboratory in Pasadena did what they always do when Voyager has a problem. They sent a command, and then they waited, because at that distance, a signal traveling at the speed of light takes more than 23 hours to reach the spacecraft, and then 23 more for the response to come back. So you send your command on a Monday morning, and you do not hear back until Wednesday. 45 hours of silence while your question crawls across the solar system, past the orbits of every planet, past the edge of the sun's influence, out into interstellar space where no human-made object has ever been before, to reach a machine about the size of a small car that was built before most of the people trying to save it were born. The command didn't work. They tried again in December. Didn't work. Tried different approaches through January and February of 2024. Nothing. For 5 months, the most distant operational spacecraft in human history sat out there in the void between stars, alive but mute, like a patient in a coma who you know can hear you but can't respond. And here is where the story gets difficult, because the people trying to fix Voyager were not working with normal tools. They had no simulator, no testbed, no development environment. The computers on Voyager 1 carry a total of 69.63 kilobytes of memory. Your phone has roughly 1 million times more. The assembly language those computers run was last actively developed in the 1970s. The original engineers who wrote the software, many of them had died. The ones who hadn't were in their 80s and 90s. The documentation, some of it was on paper, some of it was handwritten. Jeff Melstrom, the chief engineer JPL, brought in to lead what they called a tiger team, put it bluntly. The assembly language is documented, he said, but there no longer are development tools, hardware test beds, or software emulators. His team had to work, in the words of project manager Suzanne Dodd, like an archaeological dig, pulling up decades-old memos to understand code that nobody alive fully remembered writing. Think about that for a second. You are trying to perform surgery on a patient 15 billion miles away. You can only communicate once every 2 days. You do not have an X-ray machine. You do not have the patient's medical records. Not complete ones anyway. Several of the original doctors have passed away, and you cannot, under any circumstances, make a mistake, because there is no second chance. There is no reboot button. There is no roadside assistance for interstellar space. This is the story of how they fixed it. But it is also, and this is the part that doesn't get told enough, the story of why Voyager 1 exists at all, what it found when it crossed into the space between stars, and why a shrinking team of engineers has refused for almost 5 decades to let it die. Because the 22-3 crisis was not the first, and it will not be the last. Since 2022, Voyager 1 has had 3 near-death experiences, each one more improbable than the one before. each one fixed by people performing what one of them called the ultimate telesurgery on a spacecraft running on borrowed time, tended by hands consulting documents from the Nixon era. The mission assurance manager, a man named Bruce Wagner, was asked how much longer Voyager can keep going. His answer was honest in a way that engineers rarely are. "I feel good about 2030, he said, but 2035 is scary, and 2040 would be miraculous." Then he paused. "But it's Voyager, and that line, that qualifier at the end, tells you everything you need to know about what this spacecraft means to the people who keep it alive. It's Voyager, as though the machine itself has a say in the matter. To understand how we got here, to a place where humanity's farthest voice is fighting for survival at the edge of interstellar space, you need to go back not to 1977, when Voyager launched, but to 1964, to a graduate student at JPL named Gary Flandreau, and a piece of math that comes around once every 176 years. Flandreau was working on trajectory analysis for future planetary missions, and he discovered something extraordinary. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune were going to line up in a configuration that would allow a single spacecraft to visit all 4 planets by using each one's gravity as a slingshot to the next. It was like discovering that every connecting flight you needed for a round-the-world trip was departing from the same gate on the same day, and the tickets were free, but only this once. The next time the alignment would occur would be 2153, 176 years from now. If you missed it, nobody alive would get another chance. NASA designed a mission to exploit this alignment. They called it the Grand Tour. The plan was ambitious. 4 spacecraft visiting all 4 outer planets at a cost of somewhere between $750 million and $900 million. Congress took one look at that price tag in the early 1970s and killed it. This was December 1971. The Space Shuttle program was the priority, and the shuttle was devouring NASA's budget like a black hole. The Grand Tour, with all its elegance and once-in-a-lifetime timing, was dead, but not entirely dead. What survived the budget axe was a stripped-down version. 2 spacecraft, 2 planets, Jupiter and Saturn only. No Uranus, no Neptune, no Grand Tour. The cost was cut to under $360 million. They called the Mission Mariner Jupiter Saturn 1977, which is possibly the worst name ever given to a spacecraft, and thankfully somebody renamed it Voyager on March 7th, 1977, 6 months before launch. There is an irony here worth sitting with. The mission that would become the farthest-reaching, longest-lasting, most scientifically productive space exploration in human history was conceived as the cheap backup plan, the compromise, the thing Congress was willing to fund because the real mission was too expensive. If the Grand Tour had survived, we would have had 4 spacecraft. We got 2 instead, and they have outperformed every expectation by such an absurd margin that the original plan seems almost quaint in comparison. Sometimes the budget cut is the best thing that happens to a mission. Voyager 2 launched first on August 20th, 1977, on a slower trajectory that would eventually take it past all 4 outer planets, because even though the Grand Tour was cancelled, the trajectory was still there, and Voyager 2's flight path was designed to exploit it if the spacecraft survived long enough. Voyager 1 launched 16 days later, on September 5th at 12:56 UTC, from Cape Canaveral aboard a Titan IIIe Centaur rocket. It was on a faster trajectory that would get it to Jupiter and Saturn sooner, but along a path that could not be extended to Uranus and Neptune. And the launch itself almost ended the mission before it began. The Titan's second stage shut down early. Not a lot early, but early enough to leave 1,200 pounds of propellant unburned. This is the kind of problem that in most scenarios means you lose the spacecraft. The rocket does not have enough energy to put the payload on the right trajectory. And that is that. But the Centaur upper stage, the part that sits on top of the Titan and gives the final push, had onboard computers smart enough to recognize the problem. The Centaur burned longer than planned to compensate. It came within 3.4 seconds of running out of fuel. 3.4 seconds. If the Centaur had exhausted its propellant 3.5 seconds sooner, Voyager 1 would be a footnote in a NASA budget report, and humanity's farthest object would be something else entirely. But the fuel held. Voyager 1 reached space on December 15, 1977. Just 3 months after launch, it overtook its twin, Voyager 2, thanks to its faster trajectory, and began the long fall towards Jupiter. There is something worth understanding about the spacecraft itself before we get to what it found, because the engineering decisions made in the mid-1970s are the reason Voyager is still alive today, and they are the reason every crisis since has been so difficult to resolve. Voyager 1 carries 6 onboard computers organized as 3 redundant pairs. They were custom built by General Electric using discrete transistor to transistor logic and CMOS integrated circuits, the kind of technology you would find in a scientific calculator from the same era. The total memory across all 6 computers is 69.63 kilobytes, not megabytes, not gigabytes, kilobytes. To put that in perspective, the text of this script so far takes up more memory than all of Voyager's computers combined. A single high-resolution photo on your phone would overflow every memory chip on the spacecraft hundreds of times over. The command computer runs at 250 kilohertz, executing roughly 8,000 instructions per second. A modern smartphone processor runs at about 2 to 3 gigahertz and can execute billions of instructions per second. Your phone is approximately 1.75 million times faster than Voyager. But here is the thing that matters. Your phone will be obsolete in 3 years. It will be in a landfill in 10. Voyager's computers have been running continuously for 48 years in the most hostile environment any electronic device has ever operated in, bombarded by cosmic rays, baked by Jupiter's radiation belts, and frozen to temperatures close to absolute zero in interstellar space. And until November 2023, they had not missed a single day of work. The power source is equally remarkable and equally doomed. 3 radioisotope thermoelectric generators, or RTGs, each containing 24 pressed spheres of plutonium-238. Plutonium-238 is not the stuff you make bombs from. That is plutonium-239. Plutonium-238 is chosen for space missions because it decays predictably, generating heat that silicon-germanium thermocouples convert directly to electricity through the Seebeck effect. No moving parts, no turbines, no chemical reactions, just the steady atomic decay of a radioactive isotope turning nuclear heat into electrical power. At launch, The 3 RTGs produced about 470 watts. By 2025, they were producing about 220 watts. That is a loss of roughly 53% over 48 years, driven by 2 factors. First, plutonium-238 has a half-life of 87.7 years, so the raw heat output drops over time. Second, the silicon-germanium thermocouples that convert heat to electricity degrade with age and radiation exposure. The result is a power budget that shrinks by about 4 watts per year, every year, without exception. 220 watts. Think about that. Your microwave oven uses about 1,000 watts. A hairdryer uses 1,500. Voyager is running its entire spacecraft, every computer, every heater, every instrument, its transmitter, its attitude control, on less power than it takes to run 2 standard light bulbs. The high-gain antenna alone uses roughly 200 watts, which means after you power the antenna, you have approximately 20 watts left for everything else. Each remaining science instrument draws about 4 watts. You can run maybe 4 or 5 instruments and have nothing left over. And the transmitter that is Voyager's only connection to Earth, broadcasts at 22.4 watts. That is about the power output of a refrigerator light bulb, but it broadcasts through a 3.7-meter parabolic dish that focuses the signal into a beam so narrow, so tightly concentrated, that after traveling 15.9 billion miles, the signal arrives at Earth with a strength of less than 1 attowatt, that is 10 to the negative 18th watts. To receive that signal, NASA uses the Deep Space Network, a system of 3 complexes spaced around the globe, each with enormous dish antennas. The largest is DSS-43 in Canberra, Australia, a 70-meter dish weighing over 3,000 tons, equipped with cryogenic receivers cooled to 17 Kelvin, which is negative 256 degrees Celsius, about 17 degrees above absolute zero. The receivers have to be that cold because at room temperature, the thermal noise from the electronics would drown out Voyager's signal completely. And even with all of that, the data rate is 160 bits per second. To put that in perspective, a typical home internet connection is about 100 million bits per second. Voyager's data rate is about 600,000 times slower. Sending a single smartphone photo at Voyager's data rate would take roughly 5.5 days of continuous transmission. But that slow data rate is what makes the whole thing possible, because the slower you transmit, the narrower the bandwidth you need to listen on, and the narrower the bandwidth, the less noise you pick up. It is the engineering equivalent of whispering in a perfectly silent room rather than shouting in a stadium. So this is what we are working with. A spacecraft with less memory than a 1980s calculator, powered by decaying plutonium, transmitting at the power of a refrigerator bulb, crawling along at 160 bits per second across a distance so vast that light itself needs more than 23 hours to cross it. And somebody has to keep this thing alive. On March 5th, 1979, Voyager 1 arrived at Jupiter, and everything changed. The spacecraft passed within approximately 280,000 kilometers of Jupiter's cloud tops, which sounds like a lot until you consider that Jupiter is so enormous you could fit 1,300 Earths inside it. And at that distance, Voyager was skimming close enough to resolve features in the atmosphere that no telescope on Earth had ever seen. Over a 4-month encounter window, Voyager returned roughly 19,000 photographs, But photographs alone do not capture what Jupiter revealed, because what Voyager found at Jupiter was not just detail. It was surprise after surprise, the kind that rewrites textbooks. Start with Io, Jupiter's innermost large moon, roughly the size of Earth's moon, had been predicted to be a dead, cratered world, geologically inert, frozen in time. What Voyager found was the most volcanically active body in the solar system. 9 actively erupting volcanoes with plumes shooting over 300 kilometers above the surface. 300 kilometers. That is higher than the International Space Station orbits above Earth. Io was not dead. It was the most violently alive world anyone had ever seen. Its surface constantly repaved by sulfur and silicate lava, driven by tidal forces from Jupiter's immense gravity kneading the moon's interior like bread dough. This was the first active volcanism ever observed beyond Earth. The discovery was made not by the primary imaging team, but by navigation engineer Linda Morabito, who noticed the plume in a navigation photograph while checking Io's position against background stars. She was looking for the edges of Io's disk against the star field to refine trajectory calculations, a routine task. And there, on the limb of the moon, was an anomalous bright crescent that should not have been there. She almost didn't report it because she thought it might be a camera artifact, a stray reflection, a processing error. Instead, she flagged it, and the science team confirmed it was an eruption plume rising from the volcano now known as Pele, backlit by the sun. In that single observation, Morabito had discovered extraterrestrial volcanism. She was 26 years old. Voyager also discovered Jupiter's faint ring system, something nobody had expected. The ring had been theorized as a possibility, but never confirmed. It is nothing like Saturn's grand, visible rings. Jupiter's ring is thin, dark, composed mainly of tiny dust particles knocked off the inner moons by micrometeorite impacts, and essentially invisible from Earth. But it was there, and finding it settled a decades-old debate. It also found 3 previously unknown moons: Thebe, Metis, and Adrastea, tiny worlds orbiting close to Jupiter that had been invisible from Earth. Metis, the closest to Jupiter, orbits inside the planet's ring system, closer to the cloud tops than any other known moon, a small body of rock and ice completing an orbit every 7 hours, moving so fast that it circles Jupiter faster than Jupiter itself rotates. And it imaged Europa's surface in enough detail to reveal something tantalizing. Europa was covered in cracked ice, a network of fractures and ridges that looked for all the world like the ice sheets above Arctic oceans on Earth. The implication was staggering. Beneath that ice, warmed by the same tidal heating that drove Io's volcanism, there might be a liquid water ocean. In 1979, nobody could prove it, but the cracks in Europa's ice planted a seed that would grow into one of the most compelling targets for the search for extraterrestrial life. And that story is still unfolding today. But Jupiter was the warm-up. Saturn was the destination that would define Voyager 1's fate forever. On November 12, 1980, Voyager 1 swept within roughly 124,000 kilometers of Saturn's cloud tops. Saturn is, from a distance, the most beautiful planet in the solar system. The rings alone are among the most visually stunning structures in nature. A disk of ice and rock particles stretching nearly 300,000 kilometers across, but in places only 10 meters thick. If you scaled Saturn's rings down so their diameter equaled a football field, they would be about 10,000 times thinner than a sheet of paper. They are, proportionally, one of the flattest structures known in the universe. Voyager revealed the rings to be far more complex than anyone expected, with thousands of individual ringlets, gaps, waves, and structures that spoke to gravitational interactions of extraordinary subtlety. It discovered the F-ring, a narrow, braided, twisted ring shepherded by two small moons that seemed to defy the neat circular orbits astronomers expected. It found 5 new moons, including several that were gravitationally sculpting the ring structure in real time. But the encounter that mattered most happened 18 hours before closest approach to Saturn. On November 11th, Voyager 1 passed within 6,490 kilometers of the surface of Titan. That is about 4,000 miles, close enough to taste. Titan had been a mystery for decades. It was the only moon in the solar system known to have a substantial atmosphere, but nobody knew what that atmosphere was made of, or how thick it was, or what was going on beneath it. Voyager answered all 3 questions in a single pass. The atmosphere was roughly 90% nitrogen, with the surface pressure about 60% higher than Earth's. On Earth, surface pressure is 1 atmosphere. On Titan, it is 1.6. The remaining atmosphere was rich in methane and organic compounds, the kind of prebiotic chemistry that scientists suspected might be a precursor to life. Titan was a world with a thick, hazy orange atmosphere, a nitrogen pressure cooker with the raw chemical ingredients for biology. It would take another 25 years until the Huygens probe descended through that atmosphere in January 2005 to confirm that Titan had lakes and seas on its surface, not water, liquid methane and ethane. It rains on Titan, and the rain is hydrocarbons, and the lakes are hydrocarbons, and the whole place is like Earth through a funhouse mirror where the water cycle has been replaced by a methane cycle. On Earth, water evaporates from the oceans, rises as vapor, condenses into clouds, and falls as rain. On Titan, methane evaporates from the hydrocarbon lakes, rises into the thick nitrogen atmosphere, condenses into methane clouds, and falls as methane rain onto a landscape of water, ice frozen harder than granite. The temperatures are so cold, about negative 179 degrees Celsius, that water ice on Titan behaves like rock does on Earth. The mountains are ice, the bedrock is ice, and the rivers that carve channels through that ice carry liquid methane to the seas. But here is the decision that shaped everything that follows. The trajectory required to fly Voyager 1 close enough to Titan to study its atmosphere came at a price. The gravitation assist from Saturn after the Titan flyby hurled Voyager 1 upward, out of the ecliptic plane, the flat disk where all the planets orbit. Once you leave the ecliptic plane at that angle and that speed, you are not coming back. You are not visiting Uranus. You are not visiting Neptune. You are done with planets forever. The team knew this when they planned the trajectory. They chose Titan over the Grand Tour. Voyager 2 would later pick up the mission Voyager 1 abandoned, flying onto Uranus in 1986 and Neptune in 1989, completing the Grand Tour that Congress had tried to kill. But Voyager 1, after Saturn, had only one direction: out, away from the sun, into the darkness. And for the next 10 years, the darkness is where Voyager 1 went. Silently, steadily, transmitting engineering data, but doing no major science. The cameras were pointed at nothing. The planetary encounters were over. The spacecraft was still functional, still communicating, still doing its job, but the job had become simply surviving and traveling farther. Then, Carl Sagan made a request. Sagan had been pushing the idea since 1981. He wanted Voyager to turn its cameras around, not to look at anything in particular, not to photograph a planet or a moon or a ring. He wanted Voyager to look back toward the inner solar system and photograph Earth. The engineering team was not enthusiastic. Pointing the cameras back toward the sun risked damaging the optics. The image would be scientifically useless. Earth would be nothing more than a smudge, less than a pixel, barely distinguishable from noise. There was no scientific justification whatsoever. Sagan did not care about the scientific justification. He cared about the human one. On February 14th, 1990, Valentine's Day, from a distance of 6.055 billion kilometers, roughly 40 astronomical units from the Sun, Voyager 1 turned its camera and took 60 photographs of the inner solar system. One of those photographs, processed by planetary scientist Carolyn Porco and JPL engineer Candy Hansen, showed Earth. It was a point of light occupying 12/100ths of a single pixel, barely visible, caught in a band of scattered sunlight from the camera optics that made it look like a mote of dust floating in a sunbeam. The cameras were shut off permanently 34 minutes later. The data crawled back to Earth over the next 3 months, arriving on May 1st, 1990. And then Sagan wrote about what the picture meant. And those words became arguably the most quoted passage in the history of science. That's here. That's home. That's us. Every human being who ever was lived out their lives on a mote of dust, suspended in a sunbeam. I am not going to quote the full passage because you have probably read it, and if you have not, you should read it yourself, in full, in Sagan's own 1994 book, Pale Blue Dot. What I will say is this: Sagan understood something about Voyager that the engineers, brilliant as they were, sometimes missed. The mission was never only about science. It was about perspective. It was about what it means to build something that goes farther than anything you have ever built. To look back from that distance and see yourself for what you are: small, fragile, alone, and then to keep going anyway. After the pale blue dot photograph, Voyager 1 went quiet in a different sense. The cameras were off. The planetary science was over. But the spacecraft kept moving at 17 kilometers per second, roughly 38,000 miles per hour, covering about 3.5 astronomical units per year. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. Voyager was adding 3.5 of those every year, heading 35 degrees above the ecliptic plane toward the constellation Ophiuchus. The question now was whether Voyager would live long enough to reach the boundary of the Sun's domain. The Heliosphere, the bubble of charged particles that the solar wind blows out into interstellar space, extends far beyond the planets. Its edge, the heliopause, was theoretically predicted but had never been directly detected. Nobody knew exactly where it was. Estimates ranged from about 80 to 150 astronomical units from the Sun. Voyager 1 was heading in the right direction. But would the power hold? Would the instruments last? Would the computers survive? For over 2 decades, the answer was yes. Year after year, Voyager 1 kept transmitting, kept measuring, kept running on its slowly decaying plutonium. The power dropped by about 4 watts each year, and each year the team shut down something non-essential. A heater here, a backup system there. They learned to operate the spacecraft on less and less power, the way you learn to cook with fewer ingredients. You get creative or you starve. And then, on August 25th, 2012, Voyager 1 crossed the line. The evidence was sudden and dramatic. Solar energetic particles, the charged particles blown outward by the sun, dropped to nearly zero. At the same time, galactic cosmic rays, the high-energy particles that come from outside the solar system, surged. Voyager had passed from a region dominated by the sun's influence into one dominated by the galaxy. It had crossed the heliopause. But confirming the crossing took over a year, and the reason why tells you something important about how science actually works versus how people imagine it works. The models had predicted that when Voyager crossed the heliopause, the magnetic field direction would change dramatically. Inside the heliosphere, the field is shaped by the sun. Outside, it should be shaped by the interstellar medium, the thin gas and dust that fills the space between stars. Scientists expected a sharp rotation in the field direction. What they got was a change of 2 degrees, essentially nothing. The magnetic field barely moved. This created an argument. Had Voyager really crossed into interstellar space? Or was it in some intermediate region, some unexpected boundary layer that nobody had predicted? The plasma instruments that could have settled the question directly were partly broken. The plasma spectrometer had stopped working in 1980 during the Saturn encounter, so the team had to get creative. The breakthrough came from an instrument nobody had expected to provide the answer. The plasma wave subsystem detects oscillations in the surrounding plasma, essentially listening for vibrations in the charged gas around the spacecraft. In April 2013, the plasma wave subsystem detected a distinct signal. A solar eruption from months earlier had sent a shockwave outward through the heliosphere, and when that shockwave reached Voyager's position, it set the surrounding plasma ringing. The frequency of that ringing revealed the density of the plasma, and the density was roughly 80 times higher than what Voyager had measured inside the heliosphere. Inside, the density was about 0.002 electrons per cubic centimeter. Outside, it was about 0.055. That 80-fold jump was exactly what you would expect at the transition from solar wind plasma to interstellar plasma. NASA made the official announcement on September 12, 2013. Ed Stone, who had been Voyager's project scientist since 1972, stood before the cameras and said what 40 years of work had been building toward. Now that we have new key data, we believe this is mankind's historic leap into interstellar space. Stone was 77 years old at the time. He had spent 41 years waiting for that sentence. But the crossing raised more questions than it answered. The magnetic field direction, the one that should have changed and didn't, remained a puzzle for years. Eventually, a 2015 paper in the astrophysical journal Letters proposed that the interstellar magnetic field is distorted near the heliopause, warped by the heliosphere itself, like an elastic cord wrapped around a beach ball. The field only gradually returns to its true interstellar orientation as you move farther from the boundary. By around 22,000, The field was expected to finally align with the pristine interstellar direction, signaling that Voyager had moved far enough from the heliopause to sample undisturbed interstellar space, and the plasma density kept surprising everyone. As Voyager traveled deeper into interstellar space, the density continued to rise. It went from 0.055 near the heliopause to about 0.12 at 160 astronomical units, and kept climbing to about 0.147 before leveling off. This was not expected. The interstellar medium was supposed to be relatively uniform. Instead, Voyager was finding a gradient, density increasing with distance from the Sun, as though the spacecraft were moving into progressively denser material. In October 2200, both Voyagers detected a significant and unexplained density rise that might indicate Voyager 1 had entered a small cloud of ancient interstellar plasma carrying a distinct magnetic signature, a relic from some long-past stellar event drifting through the galaxy. And then there is the hum. In May 2001, a Cornell doctoral student named Stella Koch-Ocker and her colleagues published a paper in Nature Astronomy describing something Voyager's plasma wave subsystem had been detecting since mid-2017, a faint, persistent, narrow-band plasma wave emission. Not the sporadic whistles and crackles that solar shock waves produce when they slam into the interstellar medium. Those come and go. This was constant, a single tone, barely above the noise floor, humming continuously as Voyager moved through interstellar space. The hum of the interstellar medium, the background music of the space between stars. Cornell astronomer James Cordis described it in a way that captures both the science and the poetry. The interstellar medium is like a quiet or gentle rain, he said. In the case of a solar outburst, it is like detecting a lightning burst in a thunderstorm, and then it is back to a gentle rain. What Voyager is hearing continuously is the gentle rain, the baseline vibration of the thin plasma that fills the galaxy. Nobody had ever measured it before. Nobody could have without a working plasma wave instrument sitting in interstellar space for years at a time. The cosmic ray data was equally revelatory. Inside the heliosphere, the Sun's magnetic field and solar wind deflect and attenuate galactic cosmic rays. Voyager's measurements showed that the heliosphere blocks more than 70% of galactic cosmic radiation. Beyond the heliopause, Voyager measured the first ever direct spectrum of local interstellar cosmic rays down to energies as low as 3 million electron volts per nucleon. The hydrogen to helium ratio was 12.2, plus or minus 0.9. Peak hydrogen intensity was roughly 15 times what is observed near Earth. Puzzlingly, the ionization rate of atomic hydrogen in the local interstellar medium was a factor of 10 lower than what astronomers had inferred from observations of other, more distant interstellar clouds. That discrepancy is still unresolved. It might mean the local interstellar cloud is unusual, or it might mean the models used for distant clouds are wrong, or it might mean something nobody has thought of yet. Think about what that 70% shielding number means for life on Earth. We live inside a magnetic bubble blown by our star, and that bubble blocks the majority of the high-energy radiation that fills the galaxy. Without the heliosphere, the cosmic ray flux at Earth's surface would be dramatically higher. The effects on biology are not precisely known, but cosmic rays are ionizing radiation, and increased exposure drives higher mutation rates, increased cancer risk, and potential disruption of cellular processes. The heliosphere is, in a very real sense, a radiation shield for every living thing on Earth. And we did not know how effective it was until Voyager measured the difference from outside. The shielding is not constant either. The heliosphere breathes. It expands and contracts with the 11-year solar cycle, growing larger when the sun is active and producing a strong solar wind, shrinking when the sun is quiet. During solar minimum, the heliosphere is smaller, the heliopause is closer, and more cosmic rays penetrate into the inner solar system. During solar maximum, the reverse is true. Voyager's measurements from interstellar space, combined with measurements from spacecraft inside the heliosphere, are providing the first direct calibration of how this breathing affects cosmic ray flux at Earth. The answers will feed directly into climate science because cosmic rays are suspected to play a role in cloud formation, which affects global temperature. The connection is contested, and the effect, if it exists, is probably small compared to other climate drivers. But understanding it requires knowing the cosmic ray flux, and knowing the cosmic ray flux requires knowing how the heliosphere modulates it, and knowing that requires Voyager. There is also the question of what the heliosphere actually looks like. Before Voyager, the prevailing model was a comet-shaped structure, rounded at the nose, where the interstellar wind pushes against the solar wind, and elongated into a tail stretching far behind the sun as it moves through the galaxy. This model was elegant, intuitive, and almost certainly wrong. Data from Voyager and from other missions, including the Interstellar Boundary Explorer satellite, which maps the heliosphere's boundary using energetic neutral atoms, suggest a different shape. Some models propose a nearly spherical heliosphere with no extended tail. Others propose a shape more like a croissant, with two lobes created by the interaction between the solar magnetic field and the interstellar magnetic field. The debate is ongoing, and it is a debate that can only be resolved by more data from more directions, which is one of the arguments for the interstellar probe concept that would approach the heliosphere's boundary from a different angle than either Voyager. The shape of the heliosphere matters because it determines how the sun interacts with its galactic environment. As the solar system orbits the center of the Milky Way, it passes through regions of varying interstellar density, different clouds, different magnetic field orientations, different radiation environments. The heliosphere's shape and size determine how effectively it shields the inner solar system from each of these environments. Over geological timescales, millions of years, the sun has passed through dense molecular clouds where the heliosphere would have been compressed dramatically, possibly exposing Earth to much higher cosmic ray fluxes. Some researchers have speculated that these passages correlate with mass extinction events in the fossil record. The evidence is circumstantial, and the correlations are weak. But the hypothesis cannot be tested without understanding the heliosphere. And understanding the heliosphere requires the measurements that only Voyager and its eventual successors can provide. What Voyager has revealed, taken together, is that we live inside a dynamic, breathing, irregularly shaped magnetic bubble, embedded in a thin, humming plasma that fills the spaces between stars, and that this bubble protects us from most of the galaxy's radiation while letting some through in ways that vary over time and may have influenced the history of life on Earth. We knew almost none of this with certainty before August 25th, 2012. We know it now because of a spacecraft built in the 70s, powered by plutonium, transmitting at the power of a light bulb, tended by a dozen people in Pasadena. Every day, Voyager 1 keeps transmitting. It returns data from a region no other instrument has access to. The interstellar medium turned out to be denser, more dynamic, and more surprising than anyone's models predicted. And every one of those surprises deepens the argument for keeping the mission alive as long as possible. Because every day is genuinely new data about genuinely unexplored territory. But the data only matters if the spacecraft can transmit it. And by 22,000, the spacecraft was starting to fail in ways nobody had anticipated. Sometime in March or April of 22,002, the attitude, articulation, and control system on Voyager 1 started behaving strangely. The AACS is the computer responsible for one of the most critical functions on the spacecraft. It keeps the 3.7-meter high gain antenna pointed at Earth. If the antenna drifts even slightly off target, the signal weakens. If it drifts far enough, communication is lost entirely. The antenna needs to point at a specific spot in the sky with a precision of about half a degree, and it has been doing that continuously for nearly 45 years. The AACS handles this job by tracking reference stars, calculating the spacecraft's orientation, and firing tiny thruster jets to make corrections. So when the AACS started sending garbled telemetry back to Earth, it got people's attention. NASA publicly disclosed the problem on May 18, 2022, and the description they gave was unsettling. The spacecraft was still executing commands normally. The signal had not weakened, meaning the antenna was still pointed correctly at Earth. Science data was still flowing. But the AACS health data, the status reports the computer sends about its own condition, had become what NASA described as randomly generated. The data packets were technically valid, properly formatted, containing the right number of bits in the right structure, but the values inside them did not reflect any possible state the AACS could be in. It was like receiving a properly addressed letter in a correct envelope with proper postage and opening it to find the text was random words. The format was right. The content was impossible. Think about what this means from a diagnostic perspective. You have a computer 15 billion miles away that is correctly doing its job, correctly pointing the antenna, correctly executing commands, but incorrectly reporting its own status. Is the computer malfunctioning? It seems to be working fine. Is the status report wrong? It is not just wrong, it is nonsensical, containing values that don't correspond to reality. Is the transmission corrupted? The signal is clean. Every other telemetry stream is normal. Just this one computer's self-report is garbage. The diagnosis took months because every diagnostic command required a 45-hour round trip, and because the failure mode was genuinely novel. Nobody had seen anything like this in the history of the mission. Eventually, the engineering team determined what was happening. The AACS had started routing its telemetry through an onboard computer that had stopped working years earlier. That dead computer was corrupting the data as it passed through, like forwarding your mail through an office where nobody works anymore and the mailroom has been trashed. A deeper analysis, published in JPL's October 2023 update, revealed something even more concerning. The AACS had entered an incorrect operating mode, where it was misdirecting commands into memory rather than executing them. One of those misdirected commands had garbled the status report before it reached Earth. The underlying trigger was never definitively identified. The best guess was that a faulty command from another onboard computer had knocked the AACS into its incorrect mode. But which computer? Which command? Why now? After 45 years of flawless operation, nobody could say for certain. As Suzanne Dodd put it, "We're happy to have the telemetry back, but I think we may never get to the root cause." Sometimes, with a 48-year-old spacecraft in an environment no machine has ever experienced, the best you can do is fix the symptom and move on. The fix itself was almost anticlimactically simple. In August 2202, engineers sent a command rerouting AACS telemetry to the correct computer. It worked. The garbled data stopped. The clean status reports resumed. No science data was lost during the entire anomaly. Propulsion engineer Todd Barber called the remote repair the ultimate telesurgery, and he was not being entirely hyperbolic. You are operating on a patient you cannot see, cannot touch, cannot examine in real time, across a distance that light needs a full day to cross. And you have to get it right the first time, because the patient cannot come back for a follow-up visit. As insurance against recurrence, JPL uploaded a software patch to both Voyagers in October 2003. Dodd described it as like an insurance policy that will protect us in the future. The patch was designed to prevent the AACS from accidentally routing data through dead computers ever again. But the AACS anomaly, for all its drama, turned out to be the easy one, a warning shot, a tremor before the earthquake, because what it revealed was this. After 45 years of operation, Voyager's aging, partially degraded systems were beginning to interact in ways nobody had predicted. Failure modes were emerging not from individual components breaking, but from the relationships between components changing as everything slowly deteriorated. It is the difference between a single beam in a bridge rusting through, which you can inspect and replace, and the entire bridge shifting subtly on its foundations, which you cannot see until something cracks. The AACS anomaly was the crack, and the earthquake came 3 months after that software patch was uploaded. On November 14th, 2023, the flight data subsystem stopped producing intelligible output. We are back where this story started, because the FDS crisis is the one that nearly killed Voyager 1. The flight data subsystem is, functionally, the voice of the spacecraft. Every piece of data Voyager collects, from every instrument, every engineering sensor, every status report, passes through the FDS. The FDS packages that raw data into formatted telemetry frames, arranges them for transmission, and feeds them to the radio system. If the FDS stops working, Voyager might still be alive, might still be collecting data, might still be pointed at Earth with its antenna perfectly aligned, but nothing intelligible comes out. The spacecraft becomes a mute witness. It sees everything and can say nothing. What the FDS began transmitting on November 14th was a repeating pattern of ones and zeros. Not random, like the AACS anomaly, repeating the same meaningless sequence over and over, replacing all telemetry. As the engineering team later described it, the core between the spacecraft and Earth was still connected, but Voyager's voice was replaced with a monotonous dial tone. You could hear the line was open. Nobody was speaking. Suzanne Dodd was direct about the severity. It basically stopped talking to us in a coherent manner, she said. It's a serious problem. She paused and added something that mission managers almost never say publicly. It's the most serious issue we've had since I've been project manager. And it's scary because you lose communication with the spacecraft. That word, scary, from a project manager who has been managing deep space missions for decades, tells you exactly how bad this was. The AACS anomaly was a puzzle. The FDS failure was an existential crisis. JPL assembled a Tiger team, the aerospace equivalent of a SWAT team. A group of the best available engineers pulled from other projects and focused entirely on this one problem. Leading the team was Jeff Maelstrom, chief engineer for JPL's Astronomy and Physics Directorate. Maelstrom had the technical chops, but the challenge he faced was almost absurd. Start with the communication delay. Every command you send takes 23 plus hours to reach the spacecraft. Every response takes another 23 plus hours to come back. That is a minimum of 45 hours for a single exchange. If you send a diagnostic command on Monday morning, you will not see the result until Wednesday morning. If that result tells you to try something else, the next result comes back Friday morning. One diagnostic cycle per 2 days. In a normal engineering environment, you might run 100 diagnostic tests in a single day. At Voyager's distance, 100 tests would take 200 days. Now add the tools problem. There is no hardware testbed for Voyager. The original test hardware was decommissioned decades ago. There is no software emulator. The computers on Voyager use custom architecture that nobody manufactures anymore, running software written in an assembly language for which no modern development tools exist. You cannot compile new code. You cannot run it in a simulator. You cannot test it on equivalent hardware. You write the code by hand, check it by reading it line by line, and transmit it, hoping it works, because if it doesn't, you have to wait 2 more days to find out. And the documentation. Maelstrom said it himself. The assembly language is documented, but there no longer are development tools, hardware testbeds, or software emulators. The documentation he was referring to was in many cases paper, memos from the 1970s, circuit diagrams drawn by engineers who had retired or died, handwritten notes in margins. Dodd's team had a staff member whose full-time job was scanning these decades-old documents into a searchable digital system, and even that project was incomplete. They were performing software archaeology, excavating knowledge from a civilization of engineers that no longer existed. In December 2023, the team tried the most obvious fix. They restarted the FDS, sent a command to reboot the computer. It didn't work. The FDS came back up and resumed transmitting the same meaningless repeating pattern. Whatever was wrong, a reboot did not fix it. The problem was not a temporary software glitch. Something was structurally broken. Through January and February 2024, the team tried progressively more creative approaches. They cycled science instruments on and off, hoping to isolate whether a specific data stream was causing the FDS to malfunction. They sent commands to change operating modes. They tried everything in the playbook. Nothing worked. By this point, Voyager 1 had been silent, effectively, for 3 months. Every week that passed without a resolution was another week of interstellar science data permanently lost. But more than the data, the silence itself was gnawing at the team. These are people who have spent their careers in daily conversation with this spacecraft. Some of them have been listening to Voyager for longer than they have been married. The silence was not just a technical problem. It was a loss. Then someone had an idea. On March 1st, 22,004, the team sent what became known as the poke command. The idea was deceptively simple. Instead of trying to fix the FDS from the outside, they would prod the FDS into revealing what was wrong on the inside. The command reset the FDS program counter, essentially telling the computer to start executing from a different point in its software. The hope was that this would cause the FDS to try different code sequences, and that one of those sequences might produce readable output. The command was sent on March 1st. 23 hours later, it arrived. The FDS received it, executed it, and began running through different sections of its code. And on March 3rd, when the signal traveled 23 hours back to Earth, something had changed. One section of the FDS output was different from the repeating gibberish. Not all of it, just one section. But it was different. An unnamed Deep Space Network engineer, monitoring the signal at one of the tracking stations, noticed the anomaly and decoded it. What they found was extraordinary. The section of readable data contained a complete readout of the FDS memory, the entire contents of the flight computer storage dumped into the telemetry stream. It was as though the poke command had caused the FDS to empty its pockets, to lay out everything it was holding so the doctors could see what was inside. By March 10th, the engineering team had compared this memory dump against the FDS memory state from before the November failure. The comparison revealed the culprit. A single memory chip had failed. It was an RCA CD4061A, a 256 by 1-bit CMOS static RAM chip, one of many that made up the FDS memory. The chip held 256 bits, which is 32 bytes, which is an almost incomprehensibly small amount of data by modern standards. 32 bytes is shorter than this sentence, but that chip's failure had corrupted approximately 3% of the FDS memory. 256 out of 8,192 16-bit words were now unreliable, and that 3% contained a critical section of the code the FDS uses to format telemetry. Without that code working correctly, the FDS could not assemble its data into transmittable frames. It was like a postal sorting office where 3% of the sorting bins had collapsed. The letters were still arriving, but they could not be organized or delivered. Everything jammed. What killed the chip? There are two possibilities. The first is a cosmic ray strike. Out in interstellar space, beyond the shielding of the Heliosphere, the flux of galactic cosmic rays is much higher than inside the solar system. Voyager's own instruments had confirmed the Heliosphere blocks more than 70% of cosmic radiation. Without that shielding, a high-energy particle slamming into a memory chip at the wrong angle could flip enough bits to destroy it. The second possibility is simple age. The chip was 46 years old. It had been running continuously, bombarded by radiation, subjected to thermal cycling for nearly half a century. At some point, materials fail. Nobody knows which explanation is correct. It might be both. NASA announced the root cause on April 4th, 2024. But identifying the problem was only half the battle. Now they had to fix it. And this is where the story becomes, in my opinion, one of the greatest feats of engineering in the history of space exploration. Not because it was the most complex, or the most expensive, or the most dramatic, but because of the constraints. The team had to relocate the affected code to other parts of FDS memory, and there was no single spare memory location large enough to hold the entire code block. So they did something that sounds simple when you describe it, but is maddening in practice. They divided the code into smaller sections. They found empty corners of FTS memory, little pockets of unused space scattered throughout the system. They parceled the code out across these pockets, rewrote all the cross-references so each piece knew where the others were, and added jump instructions so the processor could hop from one memory location to another to execute the code in the right order. They were essentially rebuilding a house by moving the rooms to different locations and connecting them with hallways. They also needed to free up memory space. To do this, they found code that Voyager no longer needed. Specifically, code related to data rate modes the spacecraft had not used since the Jupiter encounter in 1979. At Jupiter, Voyager could transmit at 115,200 bits per second because it was relatively close to Earth. At its current distance, it transmits at 160 bits per second. The high-speed data rate code was still sitting in memory, taking up space, doing nothing, like a filing cabinet full of floppy disks in a modern office. They overwrote it, and then came the part that makes engineers lose sleep: verification. In any normal software development process, you write code, compile it, run it in a simulator, test it against expected outputs, find the bugs, fix them, test again, iterate until it works. Maelstrom's team could do none of that. There was no compiler, no simulator, no testbed, no way to run the code before uploading it to the only copy of the hardware that existed, 15 billion miles away. Verification of the code was by inspection only. That is Maelstrom's own description. They checked it by reading it, line by line, instruction by instruction. Linda Spilker, Voyager's project scientist, described engineers with circuit diagrams up on the wall with sticky notes attached, tracing the logic of the code by hand, checking every jump, every address, every reference. They went through it 3 times. Everyone was checking and making sure all the links were together. She said, "Think about what that means. You write a piece of code in a 46-year-old assembly language, by hand, without development tools. You verify it by reading it out loud to your colleagues and having them check your work, the way medieval monks used to proofread manuscripts by candlelight. And then you transmit it across 15 billion miles of space to a computer with 69 kilobytes of memory and hope that it works, because if it does not, you might never hear from Voyager again." On April 18th, 2004, they transmitted the patch. 23 hours later, it arrived. The FDS received the new code and began executing it. 23 hours after that, on April 20th, the signal reached Earth. Engineering data was flowing. For the first time in over 5 months, Voyager 1 was speaking in sentences again, not just a repeating dial tone. Actual data, formatted, structured, readable engineering telemetry. The Voyager flight team celebrated in a conference room at JPL. Spilker called it the first flight software update made to a spacecraft in interstellar space, which is technically correct and also understates the accomplishment by roughly the same margin as saying the moon landings involved some travel. But the full recovery took time. The April 18th patch restored engineering data only. Science data required additional code modifications. On May 19th, Commands went up to restore science telemetry. By May 2002, two instruments, the plasma wave subsystem and the magnetometer, were returning data. On June 13, 2024, NASA confirmed that all four science instruments were operational again. The crisis had lasted exactly 7 months from the initial failure. All data from the anomaly period was permanently lost. 7 months of interstellar measurements gone. Whatever the plasma density was doing between November 2023 and June 2024, whatever the magnetic field was doing, whatever the cosmic rays were doing, nobody will ever know. Voyager was there. It was probably measuring, but it could not tell anyone what it found. 2 days before that final announcement, on June 9th, 2024, Ed Stone died. Stone had been Voyager's project scientist for 50 years, from 1972 to 2022, the longest continuous tenure of any project scientist in the history of space exploration. Born January 23, 1936, in Knoxville, Iowa, he had grown up in a town small enough that the nearest library was a bookmobile. The New York Times described him as 5 feet 10 inches, 130 pounds, a wisp in grey. His daughter compared him to Star Trek's Mr. Spock, reserved, precise, relentlessly logical. His Caltech colleague Alan Cummings, who worked alongside him for 57 years, called him the smartest man I ever met. Stone himself characteristically deflected the praise. Becoming Voyager project scientist was the best decision I made in my life, he said. Not the best thing that happened to me, the best decision I made, as though the credit belonged to his own judgment rather than his brilliance. He had waited 41 years for the moment in September 2013 when he could announce that Voyager had entered interstellar space. He had shepherded the mission through budget cuts, instrument failures, political indifference, and technical crisis for half a century. He had stepped down as project scientist in 2022, replaced by Linda Spilker, but remained connected to the mission he had devoted his professional life to. He died at 88. His wife Alice had died the previous December. He never saw the full restoration of all 4 science instruments. The announcement came 2 days after his death. In December 2004, JPL unveiled the Dr. Edward Stone Exploration Trail, featuring 24 memorial plaques designed to evoke the golden record mounted on the Voyager spacecraft. His daughter Janet returned a spare golden record cover that Stone had kept since 2001, saying this iconic piece of space history belongs now back in institutional hands. The FDS crisis had been resolved. Ed Stone was gone. The team had barely caught its breath. And then, 4 months later, Voyager nearly died again. On October 16, 2024, the flight team sent a routine command to activate a heater on Voyager 1. This was not unusual. The team periodically fires heaters in an attempt to anneal radiation damage in aging circuits, essentially warming the components in hopes that the heat will help semiconductor crystals repair some of their accumulated defects. It is a maintenance procedure, about as dramatic as turning on the thermostat, or it should have been. The spacecraft should have had sufficient power to run the heater. But something went wrong with the power calculation, or with the spacecraft's internal assessment of its power state. And on October 16th, Voyager's autonomous fault protection system triggered. Fault protection is a set of pre-programmed emergency responses built into the spacecraft's software at the factory. When the computers detect a condition that might threaten the spacecraft's survival, fault protection kicks in automatically without waiting for instructions from Earth. Because at Voyager's distance, waiting for instructions means waiting 2 days, and 2 days might be too late. In this case, the fault protection system interpreted the heater command as a potential power overdraw and began shutting down non-essential systems to conserve electricity. This is sensible behavior for a spacecraft with essentially zero power margin. The problem is that fault protection operates on rules written in the 1970s, and those rules do not necessarily account for the current state of a 47-year-old spacecraft running on fumes. On October 18th, 2 days after the heater command, the Deep Space Network could not detect Voyager 1's signal. Silence. Again. The engineering team hypothesized that the fault protection system had lowered the X-band data rate, which would have shifted the signal frequency to a range the DSN was not monitoring at that moment. They searched for the signal at different frequencies and found it later that day. Voyager was still there, still broadcasting, just at a different rate than expected. But on October 19th, the signal vanished again. This time, the fault protection system had fired a second time, and it had done something drastic. It shut off the X-band transmitter entirely and switched to the backup S-band transmitter. Now, to understand why this matters, you need to understand the difference between X-band and S-band. X-band operates at 8.4 GHz, a relatively high frequency that allows for a tightly focused beam. The X-band antenna produces 48 decibels of gain, concentrated into a beam only half a degree wide. This is the transmitter Voyager has been using for its primary data link since the early 1980s. It is what allows a 22-watt signal to be detected across 15 billion miles. S-band operates at 2.3 GHz, a lower frequency with a wider beam. The S-band antenna produces 36 decibels of gain, with a beam about 2.3 degrees wide. 12 decibels of difference in antenna gain translates to a signal that arrives at Earth roughly 16 times weaker. But the wider beam also means the signal energy is spread over a much larger area, so the effective reduction in received signal strength is even worse than the raw gain numbers suggest. The S-band signal was, as Mission Assurance Manager Bruce Wagner explained, too weak to use long-term. The team has not been able to use it to get telemetry, let alone science data, but it allows us to at least send commands and make sure the spacecraft is still pointed at Earth. And the S-band transmitter had not been used since 1981. 43 years. It was last the primary downlink during the Saturn encounter, back when Voyager was only about 1.5 billion kilometers from Earth, less than a tenth of its current distance. Nobody knew if it still worked. Nobody could have known, because there was no way to test it without turning it on. It worked. Barely. The signal was faint, too faint for telemetry, but present. On October 22nd, the team sent a command confirming two-way S-band communication. On October 24th, NASA confirmed they had reconnected with Voyager 1 through its backup transmitter. Mission Manager Kareem Badruddin acknowledged the novelty of the situation with characteristic understatement. The probes were never really designed to be operated like this, he said. And the team is learning new things day by day. The next challenge was getting Voyager back to X-band. The S-band link was too weak to carry any useful data, and the longer Voyager operated without its primary transmitter, the greater the risk of additional full protection events cascading into an unrecoverable state. On November 7, 2024, the team successfully commanded a switchback to the X-band transmitter. The primary data link was restored. Science data collection resumed the week of November 18th, and by November 26, NASA announced that regular operations had been fully restored. 3 near-death experiences in 3 years. The AACS anomaly in 2000 and 2002. The FDS memory chip failure in 2000, 223, 2004. The fault protection transmitter switch in October 2004. Each one more improbable than the last. Each one fixed by a team that is, by any rational measure, running out of options, because the problems are not going to stop. They cannot. Voyager 1 is aging in an environment that accelerates aging. The plutonium is decaying. The power drops by 4 watts every year. The thermocouples degrade. The electronics accumulate radiation damage. The attitude control thrusters, which fire tiny puffs of hydrazine to keep the antenna pointed, are slowly clogging with silicon dioxide deposits from degraded fuel lines, and the team switched to a set of backup thrusters in 2017 that had not been fired since 1980. Memory chips can fail at any time. Heaters shut down to save power, expose other components to temperatures cold enough to damage them. Every decision to save one system risks killing another. It is a slow-motion triage, and the patient is getting sicker. 3 science instruments remain active as of early 2026. The magnetometer, which measures the interstellar magnetic field. The plasma wave subsystem, which listens for oscillations in the interstellar plasma, the instrument that detected the hum, and the low-energy charged particle instrument, which has been measuring energetic particles since launch. The low-energy charged particle instrument is scheduled for shutdown in 2226 to conserve power. The cosmic ray subsystem was already turned off on February 25, 2025. After the low-energy charged particle instrument shuts down, only the magnetometer and the plasma wave subsystem will remain. Engineers believe at least one instrument can continue operating into the 2030s. Engineering telemetry, the basic status reports that tell you the spacecraft is alive and where it is, might continue until approximately 2036. After that, there will not be enough power to run anything. And there is another problem, one that has nothing to do with the spacecraft itself. The Deep Space Network, the system of enormous antennas that receives Voyager's signal, is under immense pressure. The 3D SN complexes at Goldstone in California, Canberra in Australia, and Madrid in Spain are spaced 120 degrees apart in longitude to provide continuous coverage of deep space missions. They were built to support a handful of missions at a time. They now support dozens, and demand exceeds capacity by 40% at peak times. NASA's Artemis lunar program is expected to increase demand on the DSN tenfold by the early 2030s. And critically, DSS-43, the 70-meter dish in Canberra, is the only antenna on Earth with sufficient transmitter power to send commands to both Voyagers. It is literally the only telephone that can call Voyager. If it goes down, nobody can talk to the spacecraft. And from May 4th, 2025 through February 2026, the SS-43 went offline for upgrades. There were only brief communication windows in August and December of 2025. For most of that period, both Voyagers operated completely autonomously, unable to receive any commands from Earth. Think about what that means in the context of the three crises we just described. If the AACS anomaly had happened during the Canberra blackout, they could not have sent the rerouting command. If the FDS had failed during the blackout, they could not have sent the poke command. If the fault protection system had switched to S-band during the blackout, they could not have commanded a switch back to X-band. During those 9 months, Voyager's life depended entirely on its 48-year-old autonomous systems making the right decisions without any human guidance. That is the situation. A spacecraft running on a fraction of the power it was designed for, with computers that belong in a museum carrying instruments that are being shut down one by one, communicating at 160 bits per second through an antenna network that is overloaded and occasionally offline. And keeping this whole thing running is a team of about a dozen people. Suzanne Dodd, Voyager's 10th and first female project manager, has been with the mission since 1984. She joined as a sequencer, designing the science observation sequences for the Uranus encounter. She was 24 years old. She is now 66, and she runs both the Voyager mission and the entire Interplanetary Network Directorate, overseeing the DSN's 14 antennas worldwide. She is the person who discovered, years into her tenure, that flight software had been programmed to shut off in 2010 by engineers who had all retired. Nobody still working on the mission remembered why. She overrode the command. Imagine that. A clock you did not set, built by people you never met, counting down to kill your spacecraft. And you find it almost by accident. She once described the spacecraft to CNN with the kind of affectionate bluntness that only comes from 4 decades of intimacy with a machine. It's like flying an Apple II computer. It should be in the museum. The should in that sentence does a lot of work. It should be in a museum, but it is not in a museum. It is in interstellar space, and she's the one keeping it there. Linda Spilker succeeded Ed Stone as project scientist in 2202. She has been with Voyager since 1977, when she was a graduate student. She was there at Saturn. She was there for the pale blue dot. She was there for the interstellar crossing. She was there for every crisis. During the FDS repair, she described the scene at JPL with a kind of delight that cuts through the anxiety. Engineers with circuit diagrams up on the wall with sticky notes attached, she said, just having a great time trying to troubleshoot the 60s and 70s technology. Having a great time in the middle of a 5-month silence from the most distant human-made object, with the entire mission hanging on code, checked by visual inspection. The engineers were enjoying themselves. That tells you something about the kind of people this mission attracts. Spilker's own reflection on the mission captures its essential paradox better than anyone else's. Every minute of every day, she said, the Voyagers explore a region where no spacecraft has gone before. That also means every day could be our last. But that day could also bring another interstellar revelation. She lives in that tension between the certainty that the mission will end and the possibility that today might bring a discovery nobody expected, and she has lived in it for 49 years. Larry Zottarelli was the last original programmer who understood Voyager's antiquated computer architecture in the way that you understand your native language, at the level of instinct rather than translation. He retired in 2016 at age 80 after giving 6 months' notice to train a successor. 6 months, because the knowledge in his head could not be transferred in 2 weeks or a month or even 3 months. It took half a year of daily knowledge transfer to capture what one man had learned over 40 years of working with machines that no longer exist anywhere else. Bob Rasmussen, a software engineer who had been with Voyager from launch day in 1977, came out of retirement in 2022 to help during the AACS anomaly. He was in his 70s. Chris Jones, JPL's former chief engineer, retired in 2018, but returned that same year as a Voyager technical consultant. Joey Jefferson has been with the mission since 1978, having previously worked on the Apollo program. He bridged the two greatest exploration programs in human history with a single career. And then there is Stamatios Krimigis, known as Tom, the principal investigator for the low-energy charged particle instrument. Krimigis last saw Voyager 1 in person in the summer of 1977, a few months before launch. That was 49 years ago. He has been managing his instrument ever since, through remote commands, through data analysis, through crisis after crisis, and he has never seen the spacecraft again. His reflection on the mission's mortality is wistful. My motto for a long time was 50 years or bust, he said, but we're sort of approaching that. The team today is small, about a dozen core members. They come from remarkably diverse backgrounds: rural South Korea, the Jim Crow era American South, Mexico, Colombia. A 2023 documentary called It's Quieter in the Twilight captured their devotion in a way that press releases cannot. Director Billy Miosi observed that so much of what Voyager has achieved over the past several decades is owed to a tiny team of engineers who have forgone promotions and now retirement. They could have moved to newer missions, bigger budgets, higher profiles. They stayed with Voyager. One reviewer of the documentary wrote something that has stayed with me. Like doctors tending to patients on life support, the Voyager team is watching their patients' vital organs fail. One morning, they know they will come to work, transmit a digital good morning across the solar system, and get only silence in return. That morning is coming. It might be in 2030. It might be in 2036. It could in theory be tomorrow. Every day the team sends a command and waits 45 hours for a reply is a day that could be the last. And they do it anyway. They have been doing it for 49 years. They will keep doing it until the silence comes. But the silence, when it finally arrives, will not mean the end of Voyager, because Voyager carries something that was designed to outlast not just the spacecraft, but the species that built it. Mounted on the side of each Voyager spacecraft is a 12-inch gold-plated copper phonograph record. It weighs about 1.3 kilograms. It is encased in an aluminum cover, electroplated with an ultra-pure sample of uranium-238, an element with a half-life of 4.51 billion years, which serves as a radioactive clock. Any civilization that finds the record can measure how much of the uranium has decayed and calculate to reasonable precision how long ago the record was made. The cover also bears a set of diagrams designed by astronomer Frank Drake, explaining how to play the record. It spins at 16 2/3 revolutions per minute, half the speed of a standard LP. An included stylus and cartridge are provided for playback. Timothy Ferris, the producer of the Golden Record, guaranteed the outer surface's integrity for at least 1 billion years. The inner side, protected by the cover, for 2 billion. In 1 billion years, the Golden Record will have completed 4 orbits of the Milky Way galaxy. The Earth, by then, will have been swallowed by the expanding sun, or at least rendered uninhabitable by it, depending on which models you trust. The Golden Record will still exist, carrying its message through the dark, for civilizations that may or may not exist, may or may not find it, may or may not have ears to hear it or minds to understand it. Carl Sagan chaired the committee that assembled the record's contents. His team included Andrew Yan as creative director, Frank Drake as technical director, Timothy Ferris as producer, John Lomberg as designer, and Linda Salzman Sagan as organizer of the spoken greetings. The sound engineer was Jimmy Iovine, who would later co-found Interscope Records and Beats Electronics. He was recommended by John Lennon. They had less than a year to complete the project and a budget of $18,000. The record contains greetings in 55 languages. They begin with Akkadian, a language spoken in ancient Sumer 6,000 years ago, and end with modern Wu Chinese. One of the greetings is from Sagan's 6-year-old son, Nick, who said hello from the children of planet Earth. Between the ancient and the modern, there are greetings in Hittite, Latin, Aramaic, Mandarin, Cantonese, dozens of languages representing thousands of years of human speech. There are also greetings from a whale, because why not? If you are introducing yourself to the universe, you might as well let the other intelligent species on your planet say something too. The music selection spans human civilization with an ambition that borders on the absurd. 27 tracks. Bach's Brandenburg Concerto No. 2, First Movement, performed by Karl Munchinger and the Stuttgart Chamber Orchestra. Beethoven's Fifth Symphony, First Movement. Beethoven's String Quartet No. 13, Opus 130, the cavatina, which Beethoven himself reportedly said made him weep. Chuck Berry's Johnny B. Good, included over the objection of ethnomusicologist Alan Lomax, who argued that rock and roll was adolescent music. Sagan's response was perfect. There are a lot of adolescents on the planet. The collection also includes a Georgian folk song called Chakra Lo, a Navajo night chant, a Peruvian panpipe and drum wedding song, Javanese gamelan, an Indian raga, performed on the Sur Bahar by Sir Sri Kesar Bai Kirkar, and Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, a wordless slide guitar piece from 1927, that is. If you have not heard it, one of the most haunting pieces of music ever recorded. Johnson was a blind street preacher from Marlin, Texas, who died of malarial fever in 1945 after being denied admission to a hospital because of his race, or because he was blind, depending on which account you believe. His music is now farther from Earth than any other human artifact. The team wanted to include the Beatles' Here Comes the Sun. It would have been perfect. The Beatles favored inclusion, but EMI, which held the copyright, refused. Sagan's account, published in his 1978 book Murmurs of Earth, says EMI demanded $50,000 per record. Producer Timothy Ferris later disputed this in 2017, claiming the song was never seriously considered. The truth is contested, and both men have strong credibility. It is one of those small historical disputes that will never be resolved. A footnote that somehow captures the absurdity of human institutions. We built a message to the cosmos, a bottle thrown into the ocean of space, and the record company said no because of the licensing fee. 116 images are encoded in analog form on the record, representing life on Earth in a visual tour that begins with mathematical and physical definitions, progresses through images of the solar system and Earth's geology, and arrives at human beings, their anatomy, their reproduction, their cultures, their cities. There are images of a woman eating grapes, a supermarket, a traffic jam, and a violin with a music score. There is a photograph of the Golden Gate Bridge. There is a diagram of vertebrate evolution. There is no image of war, of poverty, of disease, or of death. This was deliberate. The record was not meant to be a complete portrait of humanity. It was meant to be an introduction, the way you put your best foot forward when meeting someone for the first time. And then there are the sounds. A 12-minute audio essay captures the sounds of Earth: rain, surf, thunder, bird song, whale songs, a heartbeat, the roar of a rocket launch, the clip-clop of horses, a tractor, a bus, a kiss, a baby's cry, a mother's first words to her newborn child. In English, the sound of an EEG machine recording brainwaves. And those brainwaves are perhaps the most remarkable thing on the entire record. On June 3rd, 1977, Anne Druyan was hooked up to an EEG machine at New York University for a session that lasted about an hour. The electrical patterns of her brain were compressed and encoded onto the golden record. She was meditating. She was thinking about history, about civilization, about the predicament of Earth. And she was thinking about being in love. 2 days earlier, on June 1st, she and Carl Sagan had been on the phone discussing the selection of Chinese music for the record. And during that call, they confessed their feelings for each other. They had known each other for years. They were both in other relationships, and on that phone call, talking about music for an extraterrestrial audience, they fell in love. So when Druyan sat in that EEG chair 2 days later, she was carrying the full weight of new love and the knowledge that her brainwaves would be riding a spacecraft to the stars. My feelings as a 27-year-old woman in love were part of what I was thinking about, she later said. It was a chance to put something more complex than a greeting on the record. Something genuinely human, not curated, not performed, not selected by committee. Just the raw electrical signature of a mind overwhelmed by the world and by someone in it. Those brainwaves are now 15.9 billion miles from Earth. They will continue moving outward at 17 kilometers per second for as long as the spacecraft exists, which, given the emptiness of interstellar space and the durability of the golden record's construction, could be longer than the current age of the solar system. Voyager 1 is heading 35 degrees north of the ecliptic plane toward the constellation Ophiuchus. In approximately 40,000 years, it will pass within 1.6 light years of a red dwarf star called Gliese 445 in the constellation Camelopardalis. It will not stop there. It is not heading toward Gliese 445 intentionally. It is simply moving through space, and Gliese 445 happens to be in the general neighborhood. After that near miss, Voyager will continue orbiting the center of the Milky Way galaxy, completing one galactic orbit every 225 million years or so, for as long as the galaxy exists. At its current speed of 17 kilometers per second, Voyager covers 1 light-year, roughly every 18,000 years. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. But Voyager is not heading in that direction. The interstellar medium through which it travels is so empty that the probability of Voyager colliding with anything significant, another star, a planet, even a substantial dust cloud, is essentially zero on any timescale shorter than the lifetime of the galaxy itself. It will drift silently through nothing for billions of years. The question Sagan posed at the end of the Golden Record project is the one that has no answer. The spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. Whether anyone ever finds the record is beside the point. It was never really for them. It was for us. The act of assembling the portrait of Earth and hurling it toward the stars told us something about ourselves that we needed to know, that we could, for a few months, set aside our differences, our borders, our wars, our licensing disputes, and agree on what mattered enough to send into the dark. Music, greetings, whale songs, a mother's voice, a woman in love, and at the center of all of it, carrying the record and the science and the fading hum of interstellar plasma and the memories of the engineers who refused to let it die, is a spacecraft the size of a small car, powered by plutonium, speaking at the volume of a refrigerator bulb, crossing the galaxy 1 light-year every 18,000 years. The fundamental insight of the Voyager mission, the thing that makes it resonate in a way that few other scientific achievements do, is not any single discovery. It is not the volcanoes on Io, or the methane seas of Titan, or the hum of interstellar space, though all of those are extraordinary. The insight is about humans, about what it means to build something and then refuse to abandon it, about the relationship between the builders and the built, the way a mission designed to last 5 years acquires a team willing to devote their entire careers to keeping it alive, the way the spacecraft's mortality mirrors the mortality of the people who tend it. John Cassani, the original project manager, the man who oversaw the design and construction of both Voyagers, was asked once about why the spacecraft had lasted so far beyond expectations. His answer was deceptively simple. We didn't design them to last 30 years or 40 years, he said. We designed them not to fail. There is a difference. Designing something to last a specific time means building in a lifespan, an expiration date, a planned ending. Designing something not to fail means building every component as well as you possibly can and trusting that quality will compound over time in ways you cannot predict. The Voyager team in the 1970s did not know the spacecraft would reach interstellar space. They did not know the RTGs would still be producing power in the 2020s. They did not know the computers would still be running after 48 years. They just built things right, and the rightness accumulated. What did building things right look like in practice? It meant redundancy at every level. 3 RTGs instead of 1. 2 of every onboard computer organized as dual redundant pairs. 2 complete sets of attitude control thrusters. 2 transmitters operating at different frequencies, X-band and S-band, either one capable of maintaining communication, 2 star trackers for navigation, redundant command decoders, redundant data storage. The philosophy was simple. If anything fails, there must be a backup. And if the backup fails, there must be a way to work around it. It also meant conservative engineering. The structural bus, the chassis on which everything is mounted, was built from aluminum and was designed with generous safety margins. The wiring harnesses used military specification connectors, rated for environments far more extreme than anything the spacecraft was expected to encounter during its primary mission. The RTG mounting booms were deployed on release mechanisms that were tested hundreds of times before flight. The magnetometer, which needs to be far from the spacecraft's own magnetic field to take accurate readings, sits at the end of a 13-meter boom, the longest appendage on the spacecraft. And that boom deployed without a hitch and has maintained its structural integrity for nearly 5 decades. The propellant tanks held far more hydrazine than the primary mission required. At launch, Voyager 1 carried about 104 kilograms of hydrazine for attitude control. The primary mission, Jupiter and Saturn, needed a fraction of that. The surplus was there as margin, as insurance against unexpected maneuvers or higher than expected thruster usage. That surplus is what has allowed Voyager to maintain antenna pointing for 4 decades beyond its planned mission. Without the extra fuel, the spacecraft would have lost attitude control years ago. The antenna would have drifted off Earth, and the mission would have ended in silence. And then there were the less tangible decisions. The choice to use radiation-hardened components where possible, even though the primary mission would only take the spacecraft through Jupiter's radiation belts once. The decision to build the software with enough modularity that functions could be redistributed across computers if one failed. The foresight to include fault protection routines that could keep the spacecraft safe autonomously for extended periods without ground contact. None of these decisions were made with a 50-year mission in mind. They were made because the engineers believed in building things properly, and because JPL's institutional culture in the 1970s rewarded quality over speed. That culture was itself a product of the Apollo era. Many of the engineers who worked on Voyager had cut their teeth on Ranger, Surveyor, and Mariner missions, programs where every failure was dissected, every anomaly analyzed, and every lesson applied to the next spacecraft. The knowledge that accumulated through those early missions, often through painful experience, was baked into Voyager's design at every level. The spacecraft is, in a sense, the inheritor of everything NASA's unmanned exploration program learned in its first 2 decades. It carries those lessons in its wiring, in its software, in the thickness of its structural members, in the quality of its solder joints. And those lessons are why it is still alive. But accumulated rightness has limits. And to understand what those limits look like in practice, you need to understand the engineering at a level deeper than most accounts bother to go. Because the crises of 22 through 2024 were not random bad luck. They were the inevitable consequences of physics, of thermodynamics, of material science, of the slow grinding reality that everything made by humans eventually wears out. The question has always been, when? And the answer to that question lives in the details. Start with the power. The 3 radioisotope thermoelectric generators on Voyager 1 are, in many ways, the most important components on the spacecraft, because without them, nothing else matters. The RTGs do not produce electricity the way a solar panel does, which matters enormously at Voyager's distance from the Sun, at 171 astronomical units. The Sun is roughly 29,000 times dimmer than it appears from Earth. A solar panel the size of Voyager's high-gain antenna would generate approximately enough power to run a wristwatch. Solar power is not an option. Nuclear power is the only option, and the specific form of nuclear power the Voyagers use is the most elegant version humans have ever built. Each RTG contains 24 pressed spheres of plutonium-238 oxide, each sphere about the size of a tennis ball, stacked inside a cylindrical housing that looks like a stubby telescope. The plutonium decays. That is all it does. It is an element that is unstable, and it relieves that instability by emitting alpha particles, helium nuclei, which slam into the surrounding material and generate heat. Plutonium-238 has a specific power of about 0.57 watts of thermal energy per gram, and each RTG contained about 4.5 kilos of the stuff at launch. Do the math, and you get roughly 2,560 watts of thermal power per RTG, or about 7,680 watts total across all three. But thermal power is not electrical power. To convert heat to electricity, the RTGs use silicon-germanium thermocouples, solid-state devices that exploit the Seebeck effect. When you have two dissimilar conductors joined at a junction, and one side of the junction is hotter than the other, a voltage develops across the junction proportional to the temperature difference. No moving parts, nothing spinning, nothing flowing, just atoms vibrating faster on one side than the other, and the difference creating a tiny electrical potential. Stack enough of these junctions together, and you can produce useful power. At launch, the three RTGs together converted about 7,680 watts of thermal power into approximately 470 watts of electrical power. That is an efficiency of about 6.1%, which sounds terrible until you remember that these generators have been running continuously for 48 years with zero maintenance, zero fuel replenishment, and zero moving parts. No mechanical power source in human history has run that long without attention. But two things are working against the RTGs, and both are relentless. The first is radioactive decay. Plutonium-238 has a half-life of 87.7 years. In 48 years, approximately 32% of the original plutonium has decayed into non-fissile products. That means the thermal output of the RTGs has dropped from roughly 7,680 watts to about 5,200 watts. You cannot stop this. You cannot slow it. It is a property of the atom itself. The second factor is thermocouple degradation. Over decades of operation, the silicon-germanium thermocouples undergo physical changes. The hot junction side, which sits against the plutonium canister, experiences sublimation and diffusion of the semiconductor materials. The cold junction side, which radiates heat into space, accumulates radiation damage from cosmic rays and from the plutonium itself. The result is that even as the thermal gradient across the thermocouples remains significant, the efficiency of conversion drops. The junctions get worse at their job. Combined, these two effects reduce the RTG electrical output by about 4 watts per year, not 4%, 4 watts in absolute terms. And because the total available power is already so low, 4 watts is enormous. It is the difference between running an instrument and not running it. It is the difference between keeping a heater on, which protects sensitive electronics from the cold of interstellar space, about 270 degrees Celsius below zero and turning the heater off, which saves power but risks freezing a component to death. The thermal management problem is in some ways more dangerous than the power problem because it involves decisions that are irreversible. When you turn off a heater to save power, the component it was protecting begins to cool. Some components can tolerate cold, others cannot. Fuel lines, for instance. The hydrazine propellant that feeds Voyager's attitude control thrusters has a freezing point of about 2 degrees Celsius. If the fuel lines drop below that temperature, the hydrazine freezes and the thrusters stop working, and the antenna drifts off target and communication is lost. Game over. So the team has to make choices. Every year, as the power drops by 4 watts, they have to decide what to sacrifice. An instrument? A heater? A backup system? Each choice is a gamble. Turning off the cosmic ray subsystem in February 2025 saved about 4 watts, but the cosmic ray subsystem was providing unique data about the interstellar cosmic ray environment. That data is now gone. Turning off the heater for the plasma wave subsystem would save a few watts, but risk freezing the instrument, which is one of only 2 science instruments that will remain active after 2026. Every decision saves the spacecraft in the short term and diminishes the mission in the long term. The team is managing a controlled decline, and they have been doing it for over a decade. The thruster story illustrates how deep these trade-offs go. Voyager 1's attitude is controlled by 16 thrusters arranged in 4 clusters on the spacecraft body. These tiny rocket engines fire pulses of hydrazine to rotate the spacecraft and keep the antenna pointed at Earth. Each pulse is measured in milliseconds. Each one nudges the spacecraft by a fraction of a degree. Over 48 years, those tiny pulses have accumulated into hundreds of thousands of firings. The original set of attitude control thrusters began showing degraded performance in the mid-2010s. The problem was silicon dioxide contamination. The hydrazine fuel passes through valves and injectors that contain silicone rubber seals, and over decades, trace amounts of silicone migrated into the fuel stream, decomposed in the combustion process, and deposited as silicon dioxide on the interior of the thruster nozzles. The deposits gradually narrowed the nozzle throats, changing the thrust profile and making attitude control less precise. In 2017, the team made a decision that sounds routine, but was anything but. They switched to a set of backup thrusters, the trajectory correction maneuver thrusters, that had not been fired since 1980. 37 years of dormancy. Nobody knew if they would work. Nobody could test them without firing them. So the team sent the command, waited 45 hours, and held their breath. The backup thrusters fired perfectly. Voyager's pointing accuracy was restored, but the backup thrusters are now the primary thrusters. And they too are aging, and there are no more backups. When the trajectory correction maneuver thrusters degrade to the point where they can no longer maintain pointing accuracy, the mission is effectively over, regardless of how much power remains, because an antenna that cannot point at Earth is an antenna that might as well not exist. This is the engineering reality that makes Wagner's words about 2030 and 2035 and 2040 so precise. He is not guessing. He is doing the math. The power curve is known. The thermocouple degradation rate is known. The thruster fuel consumption is known. The heater requirements are known. You can project forward and see with reasonable confidence when each critical system will cross below its minimum operating threshold. 2030 is the optimistic end. 2035 is the edge case. 2040 requires several things to go better than expected simultaneously. But, and this is the part that makes Voyager, several things have been going better than expected for 48 years running. To understand what that means in practice, consider what a typical day looks like for the Voyager team. And I use the word typical loosely, because there is nothing typical about maintaining a conversation with an object in interstellar space. The team works out of Building 233 at the Jet Propulsion Laboratory in Pasadena, California. JPL is a sprawling campus nestled against the San Gabriel Mountains, and Building 233 is one of its less conspicuous structures. There are no tourist plaques, no gift shop, no visitors center. Inside, the Voyager Mission Operations Room looks nothing like the dramatic control rooms you see in movies. It is a collection of workstations with multiple monitors, some of them showing real-time signal data from the Deep Space Network, others displaying engineering telemetry, others running analysis software. The room is quiet. There is no countdown clock. There are no banks of controllers sitting in tiers like a theater. It is a workspace, not a stage. A typical operations day begins with a scheduled DSN pass. The Voyager team gets allocated time on one of the network's large antennas, usually the 70-meter dish, at the complex that happens to be facing the right part of the sky at that hour. During a pass, the antenna locks onto Voyager's signal and begins receiving telemetry. The data arrives at 160 bits per second, which means a single pass of 8 to 12 hours might yield between 5 and 9 megabytes of data. That is less than a single MP3 file, but every bit of that data represents a measurement from interstellar space, and there is no other source for it anywhere in the world. If the team needs to send a command, they uplink it during the pass at 16 bits per second. The command crawls across the solar system at the speed of light, taking more than 23 hours to arrive. The spacecraft receives it, executes it, and any telemetry response travels 23 hours back. So a command sent during Tuesday morning's pass will produce a response that arrives during Wednesday afternoon's pass, assuming everything goes perfectly. This pace of interaction shapes everything about how the team thinks. You cannot troubleshoot in real time. You cannot iterate quickly. You cannot have a back and forth conversation with the spacecraft the way you might with a Mars rover, where the round-trip delay is between 8 and 40 minutes. With Voyager, every exchange is a 2-day commitment. This forces a discipline of thought that is almost monastic. Before you send a command, you think about it for a long time. You consider every possible outcome. You plan for contingencies. You triple-check the syntax, because a bad command, one that crashes a computer or triggers an unexpected fault protection response, might take weeks to diagnose and recover from, or it might be unrecoverable entirely. The team has developed over decades an almost preternatural sensitivity to Voyager's patterns. They know what the telemetry should look like, not from a manual, but from years of watching it. A slight change in the carrier signal strength might indicate a fractional drift in antenna pointing. A subtle shift in instrument noise floor might suggest a temperature change in the electronics bay. These are not alarms, they are whispers, and the team has trained itself to hear them the way a parent learns to distinguish between a baby's different cries. Hunger, discomfort, fatigue, each one sounds different if you know what to listen for. This sensitivity is what caught the AACS anomaly in 2022. The telemetry format was correct. The signal strength was normal. Everything looked fine on a cursory inspection. But the values were wrong, subtly, in ways that could only be detected by someone who had spent years staring at those specific data fields and knew intuitively what the numbers were supposed to be. An automated system might have flagged the anomaly eventually, once the values drifted far enough from their expected ranges to trigger an alert. The human team caught it immediately because the data felt wrong, even before they could articulate why. This is the kind of knowledge that cannot be written down. It lives in the nervous system, in the pattern recognition hardware of the human brain, built up over thousands of hours of watching the same data streams. And it is the kind of knowledge that dies with the person who carries it. You can train a successor. You can write documentation. You can create tutorials. But the intuitive, wordless familiarity that comes from 20 or 30 years of daily contact with a single machine, that cannot be transferred. It can only be rebuilt from scratch by someone willing to spend another 20 or 30 years doing the same thing. This is what makes the personnel situation so precarious. The dozen or so people on the current team represent the last generation with deep operational knowledge of the Voyager spacecraft. Some of them have been with the mission for decades. Some are newer, trained by the old guard, carrying knowledge that is already secondhand. When this team retires or moves on, there will be no one left who remembers what the telemetry felt like when Voyager crossed the heliopause, or who can recognize from a glance at a status screen that the AACS is behaving strangely, or who knows from experience that a particular operating mode was abandoned in 1983 because it caused a resonance in the reaction wheel assembly. That knowledge will simply be gone. The pace of Voyager's daily operations also creates a peculiar emotional rhythm. Most space missions have dramatic peaks: launch, orbit insertion, landing, flyby. The Voyager team experienced those peaks decades ago. What remains is the long plateau, the daily work of monitoring and maintaining, punctuated by occasional crises that last weeks or months and then resolve, leaving the team back where they started, tending to a slowly dying machine. It is, in many ways, more like hospice care than exploration. You are not discovering new worlds. You are not making first contact. You are keeping a patient comfortable, managing its declining systems, making the most of the time that remains. And yet the data that arrives each day is scientifically unlike anything anyone has ever seen. The interstellar medium is genuinely unexplored. Every measurement is a first. So the emotional experience of working on Voyager is this strange combination of the mundane and the extraordinary. You are performing routine maintenance on the most remote and remarkable scientific instrument in human history. The boredom and the wonder coexist day after day, year after year. There is another spacecraft in this story, and it has been running alongside Voyager 1 for the entire journey, and its experience has been both parallel and different in ways that illuminate the challenges of deep space survival. Voyager 2 launched first on August 20th, 1977, 16 days before its twin. It was sent on a slower trajectory, the one originally designed for the Grand Tour, and it visited all 4 outer planets: Jupiter in 1979, Saturn in 1981, Uranus in 1986, Neptune in 1989. Each encounter provided data that complemented and sometimes contradicted what Voyager 1 had found. And here is a misconception worth correcting, because it is one that even space enthusiasts get wrong. Most people assume Voyager 1 and Voyager 2 are flying in roughly the same direction, like two cars on the same highway. They are not. After the Saturn encounter hurled Voyager 1 above the ecliptic plane, and after Voyager 2 continued on through the ecliptic to Uranus and Neptune, the two spacecraft diverged dramatically. Voyager 1 is heading north of the ecliptic plane toward Ophiuchus. Voyager 2 is heading south toward the constellation Pavo. They are flying in nearly opposite directions relative to the ecliptic. If you imagine the solar system as a flat disk, Voyager 1 went up and Voyager 2 went down. They will never be near each other again. Voyager 2 crossed the heliopause on November 5, 2018, at a distance of about 119 astronomical units, roughly 2 astronomical units closer to the Sun than Voyager 1 had crossed 6 years earlier. The difference makes sense because the heliosphere is not a perfect sphere. It is lopsided, compressed on the side facing the interstellar wind, and elongated on the opposite side. Voyager 1 exited through a different part of the boundary than Voyager 2, and the shape of the heliosphere at each crossing point was different. But Voyager 2 had a critical advantage at its crossing. Its plasma spectrometer, the instrument that directly measures the properties of surrounding plasma, was still working. Voyager 1's plasma spectrometer had failed in 1980 during the Saturn encounter, which is why confirming Voyager 1's heliopause crossing required the creative use of the plasma wave subsystem rather than a direct measurement. Voyager 2 could measure the plasma directly, and what it found confirmed the crossing with less ambiguity. It also revealed something unexpected about the boundary itself. The transition was sharper than models predicted, a relatively narrow layer rather than a broad, fuzzy zone, and the plasma just beyond the heliopause was hotter than expected, suggesting energy transfer processes at the boundary that models had not accounted for. As of early 2206, Voyager 2 is approximately 143 astronomical units from Earth, about 28 astronomical units closer than Voyager 1. It is still returning data from its magnetometer and plasma wave subsystem. It faces the same power constraints, the same thermocouple degradation, the same thruster aging as its twin, and it is tended by the same small team at JPL. But Voyager 2 has a unique vulnerability that Voyager 1 does not share. When DSS-43 in Canberra went offline for upgrades in 2005, Voyager 2 was more exposed than Voyager 1. This is because of geometry. Voyager 2, heading south of the ecliptic plane, is only visible from the southern hemisphere. The Canberra complex is the only DSN facility in the southern hemisphere. Goldstone and Madrid cannot see Voyager 2 at all. So when Canberra goes dark, Voyager 2 is completely alone. No commands in, no commands out. Just a machine flying through interstellar space, relying entirely on its own 48-year-old fault protection systems to keep it alive. For Voyager 1, the situation is slightly less dire. Its position north of the ecliptic means all 3 DSN complexes can receive its signal. But Canberra's DSS-43 is still the only antenna with enough transmitter power to send commands to either spacecraft. So, even though Goldstone and Madrid can listen to Voyager 1, they cannot talk to it during the Canberra blackout. Listening without the ability to respond is better than total silence, because at least you know the spacecraft is still alive. But it is not much better. The DSN's capacity crisis is a story that deserves its own telling, because it is the kind of problem that nobody outside the space community pays attention to until something goes catastrophically wrong. The Deep Space Network was built in the 1960s to support a handful of missions at a time. It now supports over 40 active missions simultaneously, including the Mars rovers and orbiters, the Juno spacecraft at Jupiter, the New Horizons mission in the Kuiper Belt, the Parker Solar Probe, the James Webb Space Telescope, and both Voyagers, plus an assortment of other spacecraft spread across the solar system. Each of these missions needs antenna time. Some need daily contact. Some need continuous coverage during critical operations. And the 3DSN complexes, each with a limited number of dishes, have to schedule all of these demands into 24 hours a day, 7 days a week. The result is a system running at or above capacity nearly all the time. NASA has stated that demand exceeds capacity by 40% during peak periods. That means missions get less antenna time than they need, data transmission backlogs develop, and lower priority missions get bumped. Voyager, despite its historic importance, is a low data rate mission. It transmits at 160 bits per second. In the time it takes to download one Voyager data frame, a Mars orbiter could transmit thousands of high-resolution images. From a pure bandwidth efficiency perspective, Voyager is the least productive user of DSN resources. The argument for keeping it on the schedule is not about bandwidth. It is about uniqueness. Voyager provides data that no other mission can provide, from a location that no other spacecraft has reached, and that data will be permanently lost when the mission ends. You can always take another picture of Mars. You cannot replace Voyager's measurements of the interstellar medium, but that argument gets harder to make when Artemis missions begin in earnest. NASA's Artemis program, designed to return humans to the moon and establish a sustainable presence there, will require enormous DSN support. Crewed missions require continuous communication for safety. Lunar surface operations require high-bandwidth data links. The DSN's own planning documents project that Artemis will increase demand on the network tenfold by the early 2030s. The 70-meter dishes that currently listen to Voyager's whisper will be needed to shout at astronauts on the moon. This is not hypothetical. It is a scheduling conflict that already exists in planning documents, and it creates a scenario where Voyager's final years coincide with the period of maximum demand on the only infrastructure capable of hearing it. The irony is almost too neat. Humanity's farthest voice may fall silent, not because the spacecraft fails, but because we are too busy with our next adventure to listen. There is a broader point here about how we treat our most extraordinary achievements, and it connects back to the team that keeps Voyager alive. The Voyager mission operates on a budget that barely registers in NASA's books. The annual operating cost is somewhere around $5 million, which is roughly what it costs to produce 30 seconds of a Super Bowl commercial. For that price, you get continuous data from interstellar space, operated by a team of about a dozen people who know the spacecraft better than anyone alive. And those dozen people are, in many ways, the mission's most irreplaceable component. More irreplaceable than the RTGs, more irreplaceable than the computers, more irreplaceable than the golden record, because the RTGs will do what physics dictates. The computers will run until they fail. The golden record will endure for 1 billion years regardless. But the team is the only element that can adapt, that can diagnose an unprecedented failure, that can devise a fix nobody anticipated, that can write code in a dead language and verify it by reading it aloud and transmit it across 15 billion miles on faith. The documentary It's Quieter in the Twilight, released in 2003, brought some of these people into public view for the first time. The title comes from Voyager's mission designation. After the planetary encounters ended, the extended mission was formally called the Voyager Interstellar mission, but informally, the post-planetary phase is sometimes called the Twilight mission. It is quieter in the twilight because the spacecraft is far from everything. The team is small, and the daily work is not glamorous. It is monitoring. It is waiting. It is staring at data streams and looking for the thing that is slightly wrong, the value that is slightly off, the pattern that does not match the pattern from yesterday. The film profiles several team members whose stories have not been widely told. There is Sun Kang Matsumoto, known as Sun, a Korean-American engineer who grew up in rural South Korea and came to JPL as a young woman. There is Jefferson, who bridged Apollo and Voyager. There is the quiet dedication of people who could have been working on flashier missions, newer missions, missions that would put their names in headlines, but who chose to stay with an aging spacecraft because they believe in what it represents. Dodd has spoken about the challenge of succession planning, of training younger engineers to take over a mission built on technology they never studied in school. The assembly language Voyager's computers run has no modern textbooks. The circuit architecture has no modern equivalents. You cannot take a course in Voyager engineering at MIT or Caltech. The only way to learn it is to sit next to someone who already knows it and absorb their knowledge over months or years, the way apprentices once learned from masters. Zottarelli's 6-month knowledge transfer in 2016 was the model. But Zottarelli was the last of his kind, the last person who had been there from the beginning and who carried the original knowledge in his head. Everyone who came after him learned second-hand. Everyone who comes after them will learn third-hand. The knowledge degrades, just like the thermocouples, just like the plutonium. With each generation of transfer, some nuance is lost, some context forgotten, some instinct that cannot be articulated simply vanishing. This is why the FDS crisis was so frightening. It was not just a hardware failure. It was a test of whether the institutional knowledge had degraded past the point of usefulness. Could a team that had never met the original engineers, working from incomplete documentation in a dead programming language, diagnose and repair a computer failure on a spacecraft in interstellar space? The answer, it turned out, was yes, but the margin was thin, and the next crisis might be thinner. There is something worth considering about what Voyager has meant to the culture that built it, because the mission's scientific achievements, extraordinary as they are, represent only half of its significance. The other half is harder to measure, but arguably more important. Voyager entered public consciousness in a way that very few scientific missions have. The pale blue dot image became one of the most famous photographs in history, reproduced on posters, book covers, t-shirts, tattoos, classroom walls. Sagan's accompanying words became scripture for the secular, quoted at weddings and funerals and commencement speeches. The golden record became a shorthand for human aspiration, a symbol that even people who know nothing about space science recognize as representing something noble about the species. The mission's influence on science fiction alone would fill a book. Star Trek, the motion picture, released in 1979, featured a fictionalized Voyager probe returning to Earth after being modified by an alien machine civilization. The film was not good, but the concept was irresistible. The idea that our message might be received and answered. The Voyager record appears or is referenced in dozens of novels, films, television series, and video games. It has become part of the furniture of the human imagination, a fixed reference point for what we can achieve when we aim beyond our immediate concerns. But Voyager's cultural impact goes deeper than pop culture references. It changed how humanity thinks about its own position in the universe. Before Voyager, the outer solar system was a set of dots in telescopes. After Voyager, it was a collection of worlds, each with its own weather, its own geology, its own mysteries. Jupiter was not a striped ball. It was a turbulent atmosphere with a storm larger than Earth that had been raging for centuries. Saturn's rings were not smooth disks. They were intricate, dynamic structures of ice and rock, sculpted by gravitational forces of breathtaking subtlety. Titan was not a featureless orange sphere. It was a world with weather, with rain, with lakes, with chemistry that hinted at the preconditions for life. This transformation from dots to worlds is one of the most significant shifts in human perception since the Copernican revolution, and it was delivered not by theory or by argument, but by pictures, by data, by a spacecraft that went there and looked. There is a difference between knowing intellectually that Jupiter is a giant planet with moons and seeing with your own eyes volcanoes erupting on one of those moons, plumes of sulfur silhouetted against the blackness of space. The first is information. The second is experience. Voyager gave humanity the experience of the outer solar system, and that experience changed us in ways we are still absorbing. The Interstellar mission extended this transformation into entirely new territory. Before Voyager crossed the heliopause, the interstellar medium was a theoretical construct. Scientists had models. They had observations from telescopes. They had inferences from cosmic ray data collected inside the Heliosphere. But nobody had ever directly measured the properties of interstellar space. It was like having a theory about what the ocean floor looks like without ever sending a submarine down. Voyager was the submarine, and what it found, the density gradients, the unexpected plasma properties, the hum, the puzzling magnetic field alignment, confirmed that theoretical models were incomplete and that direct exploration reveals things that remote observation cannot. This lesson that you must go there to understand is one that space exploration teaches over and over, and that each generation has to relearn. The Mars rovers found things that orbiters missed. The Cassini mission to Saturn found things that Voyager had only hinted at, and Voyager's interstellar data is revealing things about the local neighborhood of the galaxy that no amount of telescopic observation from inside the heliosphere could have predicted. The universe is consistently more complex, more dynamic, and more surprising than our models suggest. And the only way to discover that is to send something out there and pay attention to what it reports. There is a philosophical dimension to this that is worth sitting with, because it connects to the question of why we keep Voyager alive at all. The practical argument is scientific. Voyager provides unique data. the data will be permanently lost when the mission ends. Therefore, extending the mission as long as possible maximizes the scientific return. This is a sound argument, and it is the one that appears in NASA budget justifications and mission review reports. But the real argument, the one that motivates the team, is not practical. It is existential. Voyager represents a commitment. It is a promise made in 1977 that humanity would send something out there and keep listening, would maintain the connection, would not get bored and walk away. Every year that Voyager continues operating is another year that promise is kept. Every crisis that the team resolves is a reaffirmation that we meant what we said when we launched those spacecraft. We were not just throwing hardware into the void. We were making a statement about what kind of species we are. A species that follows through. A species that tends to what it has built, even when nobody is watching, even when the funding is thin and the technology is old and the glamour has long since moved on to other things. The counter-argument is that this is sentimentality, that resources spent on a dying mission would be better allocated to new missions with greater scientific potential. And from a pure cost-benefit perspective, there is some truth to that. $5 million a year could fund graduate students, could support early career researchers, could contribute to a new telescope or a new space probe. But the counter-argument misses the point, because Voyager's value is not entirely captured by its scientific output. Its value includes what it says about us, the decision to keep tending to humanity's farthest voice, to keep listening, to keep sending commands into the dark and waiting 2 days for a reply, is a decision about human character. It says we do not abandon our creations when they become inconvenient. It says we honor the work of the dead by continuing what they started. It says that we understand, at some level, that the meaning of an endeavor is not just in its results, but in its persistence. Whether this argument would survive a truly brutal budget environment is an open question. So far, $5 million a year has been small enough to avoid serious scrutiny. But if DSN capacity becomes the bottleneck, and if Artemis missions genuinely require the antenna time that Voyager currently occupies, the decision might be made for budget reasons that have nothing to do with philosophy. The spacecraft might die not with a whisper from interstellar space, but with a memo from an administrator who needed the dish time for something else. That would be an ugly end to a beautiful mission, but it would not be the end of Voyager, because the spacecraft does not need us to keep going. It only needs us to listen. There is another misconception about Voyager that is worth addressing, because it is one that almost everyone gets wrong, including many popular science articles. The misconception is that Voyager 1 has left the solar system. It has not. Voyager 1 has left the heliosphere. It has crossed the heliopause, the boundary where the solar wind yields to the interstellar medium. It is in interstellar space in the sense that the dominant plasma around it is interstellar rather than solar. But the solar system, defined gravitationally, extends far beyond the heliosphere. The sun's gravitational influence extends to the Oort cloud, a vast spherical shell of icy bodies that is theorized to surround the solar system at distances of roughly 2,000 to 100,000 astronomical units from the sun. The inner edge of the Oort cloud is thought to begin at about 2,000 astronomical units. Voyager 1, at 171 astronomical units, has not even reached the inner edge. Think about that in terms of a journey. If you define the solar system as extending to the outer edge of the Oort cloud at 100,000 astronomical units, and Voyager 1 is at 171 AU, then Voyager has completed about 0.17% of the trip, less than 0.2%. It has, metaphorically, walked out the front door and reached the end of the driveway. The neighborhood is still ahead. The city limits are not even visible. At its current speed of 3.5 astronomical units per year, Voyager 1 will reach the inner edge of the Oort cloud in roughly 500 years, and will not exit the outer edge for about 30,000 years. It will be gravitationally bound to the Sun for all of that time, and arguably beyond, since even at 100,000 AU the Sun's gravity, though impossibly faint, still exceeds the gravitational pull of the nearest star. This does not diminish the achievement of crossing the heliopause. The heliosphere is a physically real boundary, the first one Voyager encountered, and the data from that crossing is scientifically invaluable. But the popular narrative that Voyager has left the solar system conflates two different boundaries, the electromagnetic one and the gravitational one, and it is the gravitational one that actually defines where the Sun's domain ends. There is something philosophically interesting about this correction. Voyager 1 is farther from home than any human-made object, and yet it is still, gravitationally, in our backyard. The solar system is so much larger than most people imagine that even humanity's most far-flung artifact has barely scratched the surface of it. If the solar system were the size of the continental United States, Voyager 1 would be about half a mile from the launch pad. The scale of space is not just big, it is hostile to human comprehension in a way that resists every metaphor you throw at it. At 17 kilometers per second, Voyager covers 1 light year every 18,000 years. The nearest star, Proxima Centauri, is 4.2 light years away. But Voyager is not heading toward it. The star it will come closest to is Gliese 445, in about 40,000 years, at a distance of 1.6 light years. 1.6 light years is about 15 trillion kilometers. At that distance, Gliese 445 will be a faint point of light, visible to Voyager's dead cameras only in the sense that the photons will hit the lens housing. The star will have no gravitational effect on the spacecraft. It will be a near miss in the astronomical sense, which is to say, not particularly near by human standards. After Gliese 445, the next significant stellar encounter will be in hundreds of thousands of years, and the one after that in millions. Voyager will circle the galaxy, completing one orbit roughly every 225 million years. In 1 billion years, it will have orbited 4 times. The Sun, by then, will be about 30% brighter than it is now, likely rendering Earth uninhabitable. In 5 billion years, the Sun will expand into a red giant and engulf Mercury, Venus, and possibly Earth. Voyager will still be out there. Its RTGs will have decayed to inert lead long ago. Its computers will be dead. Its antenna will be pointed at nothing. But the golden record, shielded inside its aluminum cover, will still be carrying its message. Greetings in 55 languages. Bach and Beethoven and Chuck Berry, whale songs and thunderstorms, and a woman's brainwaves recorded 2 days after she fell in love. The record was designed with this timescale in mind. The ultra-pure uranium-238 electroplated onto its cover has a half-life of 4.51 billion years, almost exactly the current age of the solar system. After 4.5 billion years, half the uranium will have decayed. After 9 billion years, 3/4, the decay products will accumulate in a ratio that any civilization capable of isotope analysis can measure, giving them a precise clock for when the record was made. The outer surface of the record itself, gold-plated copper, is expected to resist erosion in the vacuum of interstellar space for at least 1 billion years. The inner surface, protected by the cover, for 2 billion or more. What will not survive that long is meaning. The diagrams on the cover, designed by Frank Drake to explain how to play the record and where it came from, presuppose a civilization that can interpret visual representations, understand binary notation, recognize the hydrogen hyperfine transition frequency as a universal constant, and decode analog audio from grooves in a metal disc. These are not trivial assumptions. They are, in fact, enormous assumptions about the nature of alien cognition, alien sensory experience, and alien technology. Drake's pulsar map, which shows Earth's position relative to 14 pulsars, whose periods are expressed in binary, is clever, but depends on the finder knowing what pulsars are and being able to locate the specific 14 pulsars shown. Given that pulsars slow down over time, the periods on the map will become increasingly inaccurate as millions of years pass, making the map progressively harder to use. The honest answer is that the golden record is almost certainly unplayable by any civilization that finds it, for the simple reason that the probability of any civilization finding it is vanishingly small. Space is empty, truly, comprehensively, overwhelmingly empty. The distance between stars in our region of the galaxy is typically 4 to 5 light years. Voyager, even over billions of years, will pass close to very few stars. The probability of it entering a solar system with a planet harboring a spacefaring civilization that detects it and retrieves it is, by any honest calculation, indistinguishable from zero. Sagan knew this. The committee knew this. They built the record anyway, because the record was never really for the aliens. It was a mirror. It was an exercise in asking ourselves what we would say if we could say one thing to the universe, and then saying it, and then living with the knowledge that we had. And here is a question that the Voyager mission forces us to confront, whether we want to or not. What comes after? When Voyager 1 and Voyager 2 fall silent, there will be no operational spacecraft in interstellar space, nothing sending data back, nothing measuring the plasma density, the magnetic field, the cosmic ray flux. The window into the interstellar medium will close, and nobody currently knows when it will open again. This is not for lack of trying. Scientists have been proposing follow-up interstellar missions for decades. The most serious current concept is the Interstellar Probe, a mission concept that has been under study at Johns Hopkins University's Applied Physics Laboratory, the same institution that built the New Horizons spacecraft that flew past Pluto in 2015. The Interstellar Probe concept calls for a spacecraft that would travel to roughly 1,000 astronomical units from the Sun, 5 to 6 times farther than Voyager 1 is today, reaching that distance in about 50 years of flight. It would carry modern instruments vastly more capable than Voyager's 1970s technology, and it would provide the first comprehensive survey of the Heliosphere's shape from the outside, something neither Voyager can do because they each provide only a single point measurement along their respective trajectories. The Interstellar Probe was recommended as a priority by the 2230 through 2032 Heliophysics Decadal Survey, which is the scientific community's formal wish list for the next decade of sun and space weather research. That recommendation is significant because decadal surveys carry real weight in NASA's budgeting process. But a recommendation is not funding, and funding is not construction, and construction is not launch. The timeline, if everything goes perfectly, would put an interstellar probe launch sometime in the late 2030s or early 2040s. It would then take approximately 50 years to reach its target distance. That means results in the 2080s or 2090s at the earliest. So there will be a gap between the last Voyager measurement and the first interstellar probe measurement. There will be decades of silence, potentially half a century or more. During that gap, our only knowledge of the interstellar medium will come from Voyager's archived data, augmented by indirect measurements from solar system-based instruments. We will be looking at the ocean through a window, remembering what it felt like to swim. The gap matters because the interstellar medium is not static. It changes on timescales that we are only beginning to understand. The density fluctuations Voyager detected, the unexplained rise in October 2020, the slow rotation of the magnetic field direction. All of these suggest a dynamic environment with structures and variations that evolve over years and decades. A 50-year gap in measurements means 50 years of those changes going unrecorded. It is like closing your eyes during a movie and hoping you can figure out what happened when you open them again. There are other interstellar mission concepts that would reach the heliopause faster. The most ambitious is the Breakthrough Starshot initiative, which proposes using ground-based laser arrays to accelerate tiny gram-scale probes to 20% of the speed of light, fast enough to reach the nearest star, Proxima Centauri, in about 20 years. But Breakthrough Starshot is not designed for interstellar medium science. Its probes would be too small and too fast for detailed plasma measurements. They are designed for stellar flyby, for photographing exoplanets, not for the slow, patient sampling of the interstellar environment that Voyager does. The fundamental problem is that reaching interstellar space is hard, and staying there long enough to do useful science is harder. Voyager got there by accident, in a sense. It was not designed to be an interstellar probe. It was designed to fly past Jupiter and Saturn, and then it kept going because the engineers built it well and the physics allowed it. No mission currently in development is designed to replicate what Voyager does in interstellar space. The interstellar probe would come closest, but it is decades away, unfunded, and not guaranteed to happen. This reality makes every remaining day of Voyager's mission more valuable, in a way that the team acutely feels. The data Voyager collects today is not just interesting. It is the only data of its kind that might exist for half a century. The pressure to keep the mission going, to squeeze every last photon of information out of those aging instruments, is not just scientific enthusiasm. It is the knowledge that when the door closes, nobody knows how to open it again. New Horizons, the spacecraft that flew past Pluto in 2015 and the Kuiper Belt object Arrokoth in 2019, is sometimes mentioned as a potential successor to Voyager's interstellar work, but the comparison breaks down quickly. New Horizons is heading outward, yes, and it is currently about 60 astronomical units from the Sun, but its trajectory takes it in a different direction than either Voyager, and more importantly, its instrument suite was designed for planetary flybys, not for interstellar medium science. It carries a plasma instrument, the solar wind around Pluto instrument. But this instrument is designed for measuring the solar wind near Pluto, not the tenuous interstellar plasma that Voyager's plasma wave subsystem detects. New Horizons also faces the same power constraints as the Voyagers. Its RTG, a single unit compared to Voyager's 3, produces less power and is degrading on the same curve. It may have enough power to operate into the mid-2000s, roughly the same time frame as the Voyagers, but it will not cross the heliopause before its power runs out. At its current distance and speed, the heliopause is decades away. New Horizons will die inside the Heliosphere. So the picture is this: Voyager 1 in interstellar space, heading north. Voyager 2 in interstellar space, heading south. New Horizons in the Heliosphere, heading outward but not far enough or fast enough to cross the boundary before it loses power, and nothing else. After these 3 spacecraft fall silent, the deepest human presence in space will be whatever is sitting on the surface of Mars. Everything beyond Mars will be measured by telescopes, inferred from theory, and remembered from Voyager's data. The frontier will have retreated. It is a strange thing to contemplate that the farthest reach of human exploration might contract rather than expand. The popular narrative of space exploration assumes a steady expansion outward, first the Moon, then Mars, then the outer planets, then the stars. The reality is messier. We went to the Moon in 1969 and have not been back with humans since 1972. We sent Voyager to the outer planets in the late 70s and have not sent another dedicated outer planet mission with comparable scope since. We crossed into interstellar space in 2012 and have no plans to do it again before the 2040s at the earliest. The trajectory of human exploration is not a line. It is a series of leaps followed by long pauses and sometimes by retreats. Voyager's silence, when it comes, will mark one of those retreats, not because we chose to retreat, but because we did not build the successor in time. And that is perhaps the most important lesson Voyager can teach us about ourselves. Not about the interstellar medium, not about plasma physics or cosmic ray transport or magnetic field topology, but about the gap between what we can achieve in a moment of ambition and what we can sustain over the long haul. We are very good at beginnings. We are much less good at continuations. The 1970s were an era of extraordinary ambition in space exploration. In less than a decade, humanity went from the first moon landing to launching probes that would reach every outer planet in the solar system. The budget was there. The political will was there. The talent was there. And then, gradually, the budget shrank, the political will shifted, and the talent dispersed. The missions continued brilliantly on smaller budgets and with smaller teams, but the scope narrowed, the pace slowed, and the institutional knowledge, the hard-won understanding of how to build and operate machines that last for decades in deep space, began to thin. Voyager is the last living thread from that era. When it dies, the last operational connection to the golden age of planetary exploration will be severed. Cassini ended its mission at Saturn in 2017. The Galileo mission at Jupiter ended in 2003. The Voyagers are the only spacecraft still operating that were built in the 1970s, designed by the generation of engineers who learned their craft in the Apollo era and applied it to the outer solar system. That lineage, from Apollo to Voyager, is unbroken only because Voyager refuses to die. When it finally does, the lineage will end. Some of that knowledge has been captured. Dodd's scanning project, converting paper records to digital, has preserved thousands of pages of engineering documentation. The FDS crisis generated new understanding of the spacecraft's software architecture that was documented in real time. The thruster switch in 2017 and the AACS repair in 2200 and the FDS patch in 2004 all produced written records of diagnostic methods and solutions that future engineers could, in theory, consult. But documentation is not the same as understanding, in the same way that a recipe is not the same as knowing how to cook. You can read every manual ever written about Voyager's attitude control system and still not recognize, from a glance at a telemetry screen, that the AACS is routing data through a dead computer. That recognition requires what psychologists call tacit knowledge, the kind of understanding that lives below the level of conscious articulation built up through years of direct experience. It is the most valuable form of knowledge and the hardest to preserve. And when the last Voyager engineer retires, it will be gone. This is not unique to Voyager. Every long-running technical project faces the same challenge. Nuclear power plants, aging infrastructure, legacy software systems all struggle to maintain institutional knowledge across generations of operators. But Voyager is unique in the absoluteness of its situation. There are other nuclear power plants. There are other bridges. There are other software systems. There is only one Voyager 1. When the knowledge is gone, there is no second chance, no other team that can pick up where this one left off, no parallel effort in another country or another agency. The Voyager mission is singular. Its knowledge base is singular, and both are finite. The team understands this. It is why Zottarelli gave 6 months' notice before retiring, not 2 weeks. It is why Rasmussen came out of retirement to help during the AACS crisis. It is why Dodd has a person scanning documents full-time. It is why Maelstrom's Tiger team documented every step of the FDS repair in excruciating detail. They are not just fixing a spacecraft. They are trying to leave a record, a manual for a machine nobody else will ever operate, written by the last people who will ever understand it. In a sense, the team is creating their own golden record, not a message to the stars, but a message to the future, to whatever engineers might someday need to operate a spacecraft in interstellar space. Here is what we learned. Here is what worked. Here is what surprised us. Here is how we kept it alive. This is what separates Voyager from every other space mission. Every other mission has a clear scientific objective, a defined set of experiments, a planned end date. Voyager had all of those things too. Once, the Jupiter and Saturn encounters were brilliantly planned and executed. The Interstellar mission has produced groundbreaking science, but the mission's cultural meaning transcended its scientific objectives decades ago. Voyager became a symbol of something that humans rarely achieve and almost never sustain. A multi-generational commitment to something that has no commercial value, no military application, no immediate return on investment. Just knowledge, just the desire to reach farther than we have ever reached, and to keep reaching even when the reaching gets hard. The 2023 documentary captures a moment that I think about often. One of the engineers, I do not remember which, one is sitting at a console at JPL, monitoring the signal from Voyager. It is late. The room is quiet. The screens show the data stream, the telemetry, the carrier signal strength. And the engineer says, almost to himself, that one day he will come to work and the signal will not be there. He says it matter-of-factly, the way you might say that one day winter will come. Not with dread, just with the awareness that everything ends and that the ending does not diminish what came before. That awareness, that acceptance of impermanence combined with the refusal to hasten it is the emotional core of the Voyager mission. The team does not pretend that Voyager will last forever. They know exactly how much power remains, exactly how many watts per year they are losing, exactly which instruments will be shut down next. They can see the end on a spreadsheet, but they show up every day, send their commands, wait their 45 hours, and tend to a machine that most of the world has forgotten about. There are about a dozen of them. They work in building 233 at JPL, a low-slung, unremarkable structure that you would walk past without noticing. The hallways are quiet. The budget is minimal. There are no press conferences, no launch events, no splashy mission milestones to generate media coverage. Just the steady, unglamorous work of keeping humanity's farthest voice alive for one more day. Someday, probably on a day that feels like every other day, somebody on the team will notice that the signal is weaker than it should be. All the telemetry will start showing anomalies that do not respond to commands, or a DSN pass will come and go with no signal at all. The team will try everything they can, the way they always have. They will send commands. They will wait. They will consult the documentation, the handwritten notes, the memories of their mentors. They will try the tricks that worked before, the rerouting, the poking, the switching of transmitters. And this time, nothing will work. The end might come gradually, instrument by instrument, heater by heater, system by system. The spacecraft slowly going cold and dark over months or years. Or it might come suddenly, a single catastrophic failure that silences everything at once. Nobody knows which it will be. The gradual end is more likely, based on the trend of the power curve, but the sudden end is always possible. A cosmic ray in the wrong place, a fuel line that freezes, a fault protection event that cascades beyond recovery. The universe does not promise a graceful exit. When it happens, there will not be a crowd. There will not be a countdown or a ceremony, at least not in the moment. There will be a team member staring at a screen, seeing the numbers that mean the conversation is over, and quietly noting the time. There will be phone calls. There will be a press release, carefully worded, drafted long in advance, because the team has been expecting this for years. There will be, eventually, tributes and retrospectives and a recognition of what was achieved. But in the moment itself, in Building 233, it will be quiet. It has always been quiet in the twilight, and what they are sustaining is not just a spacecraft. It is a connection, the last continuous thread between Earth and the space beyond the sun's influence. When that thread breaks, there will be nothing to replace it for decades, possibly for generations. No mission, currently planned or funded, will reach interstellar space. New Horizons, now in the Kuiper Belt, is heading outward but carries no plasma instruments capable of the measurements Voyager makes. No other spacecraft has the trajectory, the instruments, or the power to replicate what Voyager is doing. When Voyager falls silent, the window closes, and we do not know when or if we will open it again. This is why the 4 watts per year matters so much. Every watt lost is not just a watt of electricity. It is a year of data that might have been. The decision to shut down the cosmic ray subsystem in February 2005 did not just turn off an instrument. It ended a 48-year continuous measurement of cosmic radiation that began inside the heliosphere and continued through the heliopause, crossing into interstellar space, the longest-running cosmic ray observation in history. From a single platform, across 2 fundamentally different physical environments. That dataset, when it is finally analyzed in its totality, will inform models of heliospheric physics and cosmic ray transport for decades. And it is finished now. There will not be another one like it. The magnetometer and the plasma wave subsystem remain. The magnetometer measures the interstellar magnetic field, the large-scale structure that threads through the galaxy, shaped by ancient supernova explosions and stellar winds and the slow rotation of the Milky Way itself. The plasma wave subsystem listens to the hum, the faint narrowband emission that Stellar Koch Ocker discovered, the constant tone of interstellar plasma vibrating at its natural frequency. Together, these 2 instruments provide a portrait of the interstellar medium that is, quite literally, irreplaceable. When the power drops below the level needed to run even one of them, the science ends. Engineering telemetry might continue for a few more years, basic heartbeat data that tells the DSN the spacecraft is still functioning and still pointed in the right direction. And then even that will fade. The signal will drop below the noise floor. The DSN will listen and hear nothing. The engineers will note the time and the date and the last confirmed signal, and they will write the final mission report, and they will close the book on the longest-running, farthest-reaching, most improbable exploration in human history. And the spacecraft will keep going. It will cross the inner edge of the Oort cloud in about 500 years. It will emerge from the outer edge in about 30,000 years. It will pass near Gliese 445 in about 40,000 years. It will orbit the galaxy silently for as long as the galaxy exists. There is nothing in interstellar space to slow it down. No atmospheric drag, no friction, no resistance, just inertia carrying it forward at 17 kilometers per second, the speed it has been traveling since Saturn's gravity flung it into the dark in 1980. Bruce Wagner's words come back one last time. I feel good about 2030, but 2035 is scary, and 2040 would be miraculous. But it's Voyager. That qualifier, that little addition at the end, it is not false hope. It is not sentimentality. It is the accumulated evidence of 48 years during which this spacecraft has survived everything the universe has thrown at it, from Jupiter's radiation belts to interstellar cosmic rays, to failed memory chips, to transmitters dormant for 4 decades. It is the recognition that Voyager has earned the benefit of the doubt, that a machine designed not to fail, tended by people who refuse to let it, has a way of exceeding the spreadsheets. In November 2026, Voyager 1 will reach 1 light day from Earth. A command sent Monday morning will not receive a reply until Wednesday morning. The distance is still growing, 3.5 astronomical units per year, and it will keep growing until the power runs out and the last instrument falls silent and the final engineering telemetry fades into the cosmic background noise. The team will be there for that. However many of them are left, they will be there. They will send the last command. They will wait the last 45 hours. They will listen for the last response. And when it does not come, they will know with the certainty that only decades of devotion can produce that they did everything they could. And then Voyager will keep going, without a voice, without an audience, through the dark, carrying its golden record and its frozen instruments and Andrew Ian's lovesick brainwaves and Blind Willie Johnson's guitar and greetings in 55 languages and the memory of every person who built it and flew it and saved it and loved it for as long as the galaxy turns.